4 of the Go Cloud Careers completely free AWS Solution Architect Associate 2024 program. And it's to prepare you for the AWS Solutions Architect certification. And this is a free AWS course that's designed to really help you start off your cloud architect career, help you with your AWS certification training, and it's fun because we get to meet each other and get to talk to you from all over the world. So if you're looking for AWS career tips, go ahead. You can ask it at some point or attend one of our free webinars. We'd love to help you. If you're interested in cloud architect training, you can join us at a webinar and we'd love to help you. But this is about passing the AWS Solutions Architect Associate Certification. The test exam is SAA-C03. So before we get back to our free AWS course, let's just do a few things so I know you're awake, alert, and oriented, so I also know that you've got access to the other things that are part of this free program. So I want to make sure that you know that we are spending a good 3 hours every day for about 2 weeks getting deep into the concept. But we're not just talking about the AWS certification concepts. We're actually getting into the technologies themselves. We'll get into these databases. As you could see, we didn't just talk about the databases that were supported like you'd find in the Solutions Architect certification. Yesterday, we really talked about a lot of the databases. We talked about MySQL, for example. We talked about Postgres, MariaDB, the Microsoft SQL Server. We talked about the Oracle options. And then we introduced the concept of NoSQL databases yesterday. And now we're going to talk about some of the NoSQL databases that are there. So we're going to have lots and lots of fun. So I'm thrilled that you are here. We have about 40 plus labs that I'd like you to do outside of this course. You know, here's the thing. After interviewing 6,000 plus technology professionals, I can find anybody out there who can click a couple of boxes and build something. But what I can't find is someone that knows why they're building it or what the technology is or how that technology works and when that organization should use it. So we're focusing a lot more on that now, because clicking the boxes is easy. And, you know, you can easily read the vendor documentation on how to do it. And also while you're at it, you know, do those free labs that we're providing. Do it on your own time. So I want to know where you're from. Let me know where you're from in the chat box. I see some people in South Africa so far. I see some people in Cameroon so far, only because I know where you're at. I see some of these names I know, for example, are in Miami. I know some of these people that are here from experience by the names are in India or Mexico, but I know a lot of you are from all over the world. So let me know where you're at. I also want to let you know that we've got a guide on which certifications can assist you in your cloud architect career. So please download that guide. It is completely free and it's going to be in the description of this video. So I want to make sure you actually get that. So now we're going to start beginning. So give me a hashtag AWS SAA, Sierra Alpha Alpha. Welcome, Samuel. Welcome, Anna Marie. Good to see you again, Samuel. Miguel, thrilled you're here. Tyrone's over there in Cape Town. He works for us. He's a rock star. Derek, I am always so happy to see you. Thanks so much. Nate Ricks, One Love. That's, you know, I love Bob Marley, so it's a song that I absolutely love, and I feel that way myself. Cyprus, Texas. Hasnat, that's pretty interesting. And George, yes, I do remember you're in Miami because we're local. And Mark, I know you're in San Francisco. AP in San Jose. I used to go out there every week. And Ben Kim in New Jersey. I lived there for a while. Adrian in Phoenix. I love this. Miguel in Colombia. I haven't been to Colombia in a while, but it's really nice. And Nigeria, fantastic. We've got a lot of Nigerian people in Baltimore, Maryland. That's the place I worked for. And Toronto, fantastic. And Chesapeake, Virginia. Boy, that's a nice place, Nate. And Anna's in Argentina. That's another really beautiful place. Sao Paulo, Brazil. Michelle, Leo for our team works there. And Miami. Yeah, Miami's a great place. Lagos, Nigeria. That's awesome. And Preb is over there in Sacramento. And another person in Nigeria. I love this. I love how global we are. And another person in Nigeria. Samuel, that's absolutely wonderful. This is great. And Colorado, I've spent some time there. And I'm seeing these AWS SAAs are coming in. The AWS Solution Architect Associate. Thank you, Mark. Thank you, Miriam. And thank you, Samuel. So Ben Kim as well. I know you're awake and alert and oriented, so now we can get into the fun. I just had to make sure nobody was sleeping. Come from healthcare, and in healthcare, we always check, the person's orientation to person, place, or time. So I know where you're from, and I know that you are here and present. So let's get into the fun. And Mark, always wonderful to see you as well. So let's talk about DynamoDB. And here's the thing. DynamoDB, which we're going to begin with, is a wonderful database, but it is an Amazon proprietary database. Given that 98% of customers in today's world are multi-cloud, Dynamo database is something you probably won't use in the real world multi-cloud environment. Not because it's not an awesome database, because it's really good, but there's certain databases that you can put in all your clouds at the same time. And DynamoDB is just not one of them. But let's talk about it anyway, because there are certain use cases where you may want to use it. Especially if you've got a customer that for whatever one reason, maybe availability isn't critical to them. Maybe they prefer simplicity. They might find them in just AWS. And they may want to use these proprietary tools because they're easier to use, lower on the maintenance and the overhead side. So let's talk about DynamoDB. It is a fully managed NoSQL database, proprietary database by AWS. Fully managed means you don't have to think about your servers. You don't have to think that much about your storage infrastructure or performance. It's done for you. You're not patching hypervisors. You're not patching the BIOS of your servers or any of that stuff. Bear with me for a second. Okay, so there's some simplicity and elegance with this. Amazon will manage the operating system, the servers, the theoretical security in that system. DynamoDB is going to be stored on high-performance SSD storage, so it's going to be as good as you're going to get in the cloud. And it's a fully managed system that's designed to deliver fast and predictable performance. And because it's a NoSQL database, that's going to scale, and it's going to scale real well, like all of them. Now, they say DynamoDB has low millisecond latency. Every millisecond counts. And you can use this DynamoDB accelerator, which is going to be an in-memory cache, that can lower the latency to sub-millisecond if the data is frequently accessed and it's going to hit the cache. DynamoDB will encrypt all data by default, and you can back it up with almost no performance on the database performance, which is great. It can be set up for global cross-regional replication, meaning you have it in the US and then you have it in Europe, and they just synchronize themselves, which you could do with pretty much any database that you would work with. And DynamoDB typically uses tables, which are collections of data, that has items, which are going to be individual records in the table, very similar to rows in a relational database. There will be attributes, which are going to be data elements within an item. And again, that's going to be similar to the columns in a relational database. We will have a partition key, and that's going to be a single attribute. And the value of the attribute is going to be hashed to determine the partition or the location of where the data is stored. DynamoDB will have something called the composite key, which is going to consist of two attributes, which are going to be the primary key and the sort key. And this is going to enable an organization to have multiple items or with the same partition key, but they're going to have different sort keys. If you're familiar with NoSQL databases, you know what I mean. DynamoDB supports secondary indexes, which means you can run queries on the 9 primary key attributes. So it'll give you lots of flexibility in querying the database. It also has the concept of a local secondary index, which will use the same partition key as the primary key, but it's going to allow, querying the database on a different key. Now, DynamoDB can support a fair number of data types, string data, numbered data, binary data, Boolean data. It can, support that like a list or a mass document type. And it can, for the set types that it can support, it's typically string sets or number sets or binary sets. Now, when you're dealing with DynamoDB, there's 2 ways you can kind of set it up. You can use auto scaling, which is going to give you capacity as needed. Or you can use provision throughput, where you tell it exactly what you need and it's going to be there for you. As a rule, if it matters, you need to know what you need ahead of time, so provision it. If you don't know what you need, that's when you would use something like an auto scaling. Now, there is an opportunity to deploy a cache. They call it the DAX, or the DynamoDB Accelerator. And that's going to be an in-memory cache to reduce read load on your systems. DynamoDB can capture changes to items in the table, for example, and you can integrate it with, say, AWS for real-time processing. If you needed to have these atomic type transactions that would adhere to, say, the ACID profile, like a relational database, where things are instantly consistent, you can do that. You can ask DynamoDB to be instantly consistent, but then anytime you make a NoSQL database instantly consistent, you're going to lose some of the scalability. And you're using these databases because they're more flexible, and they're more flexible because they also scale better. They scale better because they're not immediately consistent, so it reduces the overhead burden quite a lot. So where would you use DynamoDB? In the same place as you use any other NoSQL database. Gaming. High-performance gaming applications with a lot of data. IoT devices, you've got millions of these things out there, little weather sensors, and they're out there, and they're coming into a database generating constant data. Website management, content management, store large amounts of content like a social media provider could do. Of course, they're most likely going to use an open standard. So, some best practices with DynamoDB are to be efficient with your primary keys. Design the primary keys to evenly distribute the data across the partitions. Use indexes to optimize query performance. Plan your capacity ahead of time. Well, understand your read-write capacity units so you can provision it and provision it properly so it'll be there exactly what you need when you need it. Model your data. So model your data to minimize the need for scans and maximize the use of queries. And I hope that sort of makes sense. So next, Amazon has a quantum ledger database. We will talk about open standard databases too. The Amazon Quantum Standard Database, again, is another fully managed database. It's going to be a ledger database. And it's designed to provide an immutable and cryptographically verifiable transaction log, meaning the log and history will be there over time. The quantum ledger database is really good for applications that require transparent, permanent, and cryptographically verifiable histories and changes to data. So think about a financial transaction. You want to know it hasn't changed. Or supply chain tracking. If some product is delivered or at a location, you want to know that it's going to be there. So the key with Quantum Ledger to remember it's immutable. So it's not going to allow your data to be written over. That's why we'd use it. And how do you verify data that hasn't changed? Well, it uses cryptography. And specifically, it uses a hash to prove that the data is what it's supposed to be and it hasn't changed. And Quantum Ledger Database is an Amazon thing, but remember, it's managed. So they manage the infrastructure, the scalability, the backups, the maintenance. And, there is an advantage to using a managed service. You spend less time focusing on your infrastructure. Of course, you lose control. And it makes it harder for you to leave things when you need to. But, everything is a strengths and weaknesses, and architecture is about evaluating all the trade-offs between your options and choosing the best one for the needs of that specific business. Some things to think about, key features with Quantum Ledger Database is it's got very flexible querying. It supports SQL or PartyQL. So you can really query your data fairly easily. It automatically scales. And, it's about as high as availability as your cloud provider is going to be because they're managing it in multiple availability zones. So you have that. You could use this for supply chain management to make sure that a product hasn't been stuck. Financial transactions, I mentioned. Potentially, you could use it for a healthcare record because it's tamper-proof. Anytime where you need compliance and audit requirements, things for a government public sector like a land permit, you don't want that kind of stuff changing. So I think that can be helpful. So let's talk about how do we optimize our certain databases. What can we do? So we're going to talk about how to scale relational databases, and we may get to it later. There are open standard databases that you can use for NoSQL databases. For example, MongoDB, you could put your database servers in 3 different clouds. Apache Cassandra, you could also put your database in multiple clouds and data centers all at the same time. Now, Apache Cassandra can write to all nodes, and therefore If you've got a very high write load, no SQL database, typically speaking, Apache Cassandra is what organizations use. If you've got a very high read load database, MongoDB gives you some incredibly good performance for that. And that's typically one of the things that organizations use to select each database. But there's other options too. So let's talk about some of the Amazon database optimizations. We'll talk about backups. We'll talk about how to scale things, etc. And we'll begin with backing up. So backups, when you use any of the AWS relational databases, and this could be MySQL, it could be Postgres, it could be DynamoDB, it could be anything. When the systems do their backups, they actually take your entire virtual machine and turn it into an image. So if any of you are familiar with commercial imaging software, Symantec had a product like Ghost. There's a couple of other, there's many other options that are there, like Marconium has an instance. But what you do is you take up the hard drive or the virtual hard drive, like the block storage drive, and it creates a little bit by bit identical copy in the form of an image. And that all that's necessary is take that image and relaunch a virtual machine. Kind of like taking the file that you have for a virtual machine in a VMware environment and moving that file to another server. So it does a very good automated backup, anything on AWS. Best kind of backup, honestly, you can do. And businesses use this kind of backup and software to do this themselves, but this happens automatically, which is pretty nice. Now, a backup will typically happen during a defined window each day. And when the systems are being backed up, as a rule, temporarily, for a very short period of time, the database storage may not be available, so it might not read or write for a short period of time. And it could also just degrade the performance of the database during the backup process. So you can also do a database snapshot. And you can manually tell your beta database, back up right now. And that will give you a point-in-time copy of everything that's on that block storage volume that you have. And it'll be maintained until you delete it. Now, what it really looks like, and I love these kinds of image systems, and I've been working with imaging systems for backups for decades because they're super effective. Here's an example of what you can see. So you'll have your database, and it's going to become just one file. And here's the thing. You've got that one file. And from there, poof, you can launch another virtual machine. So another database with all your data. So I tend to love that. So here's the thing. When you've got an image and you restore it, it's going to boot up a new virtual machine. So if the IP address on my current virtual machine is 10.1.2.3/24, or let's say it's a cloud one, so we'll use a higher number. We can't use the first few. So let's say it's 10.1.2.10/24 is your IP address. That's your image. When you relaunch the image, it's going to be in a new virtual machine. So if the image comes up in a new virtual machine, when you reboot or reset your database from the image, it's going to have a new IP address. And it will also have a new DNS name. So if you've got application servers pointing to the database, you're going to have to change that DNS name or the IP address that they're pointing to. And it usually is a DNS address for lots of reasons. So what's it going to look like? You take that database image, you launch it into a virtual machine, and poof, it's up. So if you're familiar with the concept of an AMI, that's an image of the system. If you've ever downloaded an operating system, like Windows or Ubuntu or something like that, and you get a .iso file, and then you take that ISO file and turn it into a bootable drive with all the install files, that's a system image. So that's really what we're talking about. Now, when we're talking about these databases, we want to encrypt them, right? We don't want to leave data on the database unencrypted. That'd be ridiculous. So what we can do is we can encrypt the storage volume, the block storage volume, or the EBS volume where the database's data is, and poof, your data is encrypted. Now, this is going to be done with the AWS Key Management Service. And we talked about the AWS Key Management Service earlier about how that, realistically speaking, basically can help you manage the keys that are used for encryption, decryption, that sort of thing. Now, AWS, thankfully, also can support what's called transparent data encryption. And if you're using one of the more industrial databases like the Oracle database or the Microsoft SQL Server database, they're going to support what's called transparent data encryption, and it's typically done with the Cloud HSM module. So here's what transparent data encryption is. The data is encrypted on demand and decrypted on demand. So you write it to storage. When it's written to storage, it's going to be encrypted. And when you access it, it's going to be decrypted so you can access it. And then when it goes stored, it goes back to being decrypted. And that's in addition to just, being able to encrypt a storage volume. And a Cloud HSM is going to be a hardware device. We'll talk about it for managing hardware keys. So when you think about that and you can encrypt when it's stored, you can also encrypt in transit. So if the data is encrypted when it's stored, decrypted when you access it, what you're accessing is not encrypted along the wire to you to them, or encrypted as it traverses the Amazon network, or encrypted as if you were to access over the internet. So you can also do what's called encrypted in transit. So you got encrypted storage, it comes out unencrypted, TLS encrypts it on the way to you, TLS then decrypts it when it gets to you, and then it's there. So how do we use any kind of TLS protocol? Well, there's these SSL certificates we tend to use. So let's talk about scaling our databases. So in today's world, databases are, realistically speaking, a mission-critical business application. I mean, as much as you can think of it, they're everywhere, right? So they need to perform. So how do you scale your database? Well, we've got the concept of vertical scaling and horizontal scaling. So scaling up or vertical scaling is very simple. My current server has 128 cores and 2 terabytes of DRAM. I move it to a 256 core server with 4 terabytes of DRAM, and I've got more power. So that's the easiest way to scale. But I can promise you, no matter what you do in a global enterprise environment, there's often no server that can handle an organization's database. You might need a bunch of them. So that's where we talk about scaling out. And some databases enable us to scale out a lot better. For example, Apache Cassandra, we can just add 100 of these 100 different servers, and they just glue together very easily. And they write on all nodes. Oracle's got some incredible scale out performance. It's unbelievable. And other ones, like most of the relational databases, don't scale that way. So we're going to talk about how we scale relational databases. But just understand that no matter how much you go up in size of a server, at some point it's not going to be enough. So we're going to have to get into this horizontal scaling as well. So let's talk about scaling certain databases. NoSQL databases like Apache Cassandra, we can scale them via partitioning the database. And partitioning the database chops the database into multiple portions. And then the application itself has the intelligence to route between which and the partitions are there portions. So that's one way to scale it. Now with Cassandra, we can also add more servers. So Cassandra scales real well. And but that's really what we're talking about with partitioning. And you can partition a relational database or a NoSQL database. Now, scaling out relational databases is going to be very different than scaling out NoSQL databases. With Apache Cassandra, I just add new database servers, and it's so easy, and it scales so much. But for the most part, most relational databases don't work like that. Oracle's got the ability to do more, but most relational databases don't work like that. So we're going to divide our databases into read traffic, write traffic, and we're going to have to get a little creative in how we actually enable the relational databases to scale. But that's okay. I'm going to teach you how to do it. So let's talk about reading versus writing. Writing to the database is taking in the information. Reading to from the database is when you guys, ask questions of the database. So right now, I'm giving a presentation. I don't know, about 7,500 people have seen this presentation at some point during this week. And as I'm giving a presentation, which takes a lot of effort, and I'm thrilled to do it and honored to do it and privileged to do it to help you all, but it takes a lot of effort, People are asking questions in the chat box, and that's great. I want you to, but do you really think I can give 100% of my effort into giving a presentation and then answering questions in the chat box? No, it's not possible. So you see some real rock stars from my team, like Christopher Johnson, like Tyrone, like Eddie, who lives in Cameroon, in that chat box. And when you guys ask questions, they will take those questions, collate them, and then give them to me when I can actually pay attention on answering them. Well, we have to do the same thing for the database. So what we will do is we will divide our read work and our write work, because at some point it's impossible to do just both. So we're going to talk about what is a read replica, and then I'm going to show you how we use them. But for right now, you can think of Christopher Johnson and Eddie and Tyrone in that audience as a read replica. They're far more than that, but we'll call them read replicas for right now. So what is a read replica is we take our entire database and we make a basically identical copy of the database. And when we point our queries, our questions to the identical copy. So ask the copy database information about that you have, and the primary database can then focus much more on writing information. And these two are synchronized in near real time. So we reduce read load with read replicas, and I'll map it out architecturally for you so you guys and gals all really get it. Now, you can look at it this way, and this might help you look at it. And we're going to go through much more examples. But let's say you have a basic 3-tier application where you've got a web server or multiple web servers serving up web content. You have the application servers running the business logic, and then our transactions are going to be logged on these read replicas. I'm sorry, on the database. So the transactions will be logged in that RBS DB main, and we will push the same information to the read replicas. So basically they're going to able to respond to the queries or the reads. I'll map it out for you. We'll do a little architectural mock-up. But when would you use a read replica? When there's read activity, a lot of read activity. If I have 4 times the read activity than I have write activity, I need to use 4 times as many read replicas as my primary database. Now, if query traffic to the database is not slowing the database down, we might not need this. But if the database is busy and it needs help, add a read replica. So keep that in the back of your mind. Now, read replicas are not for disaster recovery. They are used for performance to offload the read load. Now, the next thing we're going to talk about is caching, and then we'll map it out and design an architecture together around this. Caching is when you put something in front of the database that when people access the same information, the cache answers. So we walked through various forms of caching earlier, but again, we'll do it again when we map it out architecturally. But here's the thing. Let's say I have a NoSQL database right now, but let's keep it. And what I have is a photo of Katy Perry and Taylor Swift's cat on it. And that was part of an Instagram post. And Katy Perry and Taylor Swift go out there. I know these names because my wife likes the two of them, and she dragged me to both of their concerts, and I do whatever my wife tells me. But that's neither here nor there. They both tweet a photo of their cat. And apparently it makes it to all the newspapers about their cat tweeted photo. So, you know, all the Katy Perry and Taylor Swift people want to go see this cat because they posted it. And any cat cuckoo like me that loves cats also wants to go see the cat because they likes the cat people. Now, imagine 10 million people go look at this cat. You know, if it was a web environment, if we put the cache there, only the first few people would actually, depending upon where they're at in the world, would request a photo of the cat. The cache would store the cat in memory, and every time somebody wanted to see it, the cache would answer, and the web servers would be relaxing. It's the same thing we're doing here with database caching. So we're going to do database caching to smooth out read load. So read replicas, offload the read work from the database, and caching could potentially reduce the read load on the read replicas. Now, here's the thing with caching. If Joey is looking for one thing, and Sally is looking for something else, and Maria is looking for something else, and Aguilo is looking for something else, and Apostoli is looking for something else, then the cache isn't going to come into play. It's only when people are looking for the same thing. So if the people requesting the queries are all requesting additional different things, and you add a cache, the cache is going to slow your performance, not improve your performance. So this is why you can never design an architecture without knowing what your use is and how people are going to use it in your traffic patterns. So we have to figure out this on a case-by-case basis. So we'll talk about this, and I'll give you an example of what this looks like. In this case, you'd have your web servers and your app servers. And you can see we've got a primary and a backup in different availability zones. And we stick a cache directly in front of the database. So when it comes to caching, understand most people use either a Redis cache or a memcached. And if you wanted to basically build your own virtual machine cache and stick it in AWS and stick that same virtual machine in Azure and the same one in Google, you could. And that's what we do in private clouds and multi-clouds and all kinds of things. But if you were in AWS and you wanted a fully managed cache, if your use case supports caching, well, AWS has a fully managed cache for you. And of course, which are your two options? A Redis cache or a memcached, because it's just them running basically caching servers for you to help improve the performance of your systems. The difference is they manage the servers, which means you don't have to think about patching the operating systems and everything else because they do it for you. But you lose control, or you do it yourself and you have control. Your use case will determine what's appropriate for you. Now, when it comes to choosing between Redis or memcached, both options work. Generally speaking, Redis offers many more features, some real advanced data structures, very high availability, cool replication, failover, session persistence, and memcached is going to be simple, but it's still high performance, but it's very simple. So it's a lower featured set type cache. So let's think about some use cases where you might use these. Let's say you want to speed up some application things. You might tend to use a cache like this. You want to get some real-time memory analytics. This will, because it's an in-memory database, actually, it'll give you some fast processing and analytics. Maybe you want to have a gaming leaderboard where people are playing different games and the scores are constantly changing. It could be used something like this. So lots of use cases for something like this. We could use it with relational databases. We can use it with NoSQL databases. We can technically use it in a serverless environment as well, like with an AWS Lambda function, because we could use, like, say, Elasticache to quickly access data in a serverless application. And, by using the cloud providers managed cache, you're going to get, alarms for performance and things in CloudWatch. If all this stuff is on your own, you could ultimately use different, more commercial packages as well to manage these things across clouds. So we talked about read replicas, which is basically offloading read load. And then we talked about caching to offload read load. What about write load? So this is going to bring us into queuing. So imagine this. Imagine you've got millions of messages coming at you in a second, and you're catching them as fast as you can, right? You're getting them, and then you miss some. Why would you miss some? Because maybe your hands can't keep up with all the balls that you have to catch if things are coming at you, okay? So there's a couple of ways that we could actually deal with this. What if I threw you the first ball, thought you caught it, gave you the next ball, you caught it, and then I sent you the third ball? Would that be easier? So imagine how much work you'd have to be going back and forth, trying to catch things and jump all over the place. Your heart rate would go up, right? You'd start to sweat. You'd get out of breath. You'd get tired. Well, basically the same thing happens to the computer. They get too many messages coming in. The CPU hits at 100%. The CPU hits at 100%, and everything ceases to function. And it's the equivalent of dropping all the balls. So how do we deal with it? Throw one ball at a time. As soon as you get it, I give you the next ball, I give you the next ball, I give you the next ball. That's queuing. Queuing is basically forming a line and getting the things when you're ready. So when it comes to scalability, often decoupling things makes it better. You saw how we talked about scaling the data center by putting the storage in one part of the data center and the servers in another part, and using block storage, connecting it over the network. Well, same thing here. So what queuing does is a way to schedule your messages, which keeps you from losing messages, which is a very good thing. And it keeps the CPU down, which means your databases can scale even more. Offload the read work, offload the catching the balls until you're ready to do it. You're going to get a lot less sweaty and a lot less out of breath. See, here's how it works. The sender sends a message into the queue, and it hangs out in the queue. And as soon as the receiver is ready for it, it pulls the message from the queue. And then the queue drops the message after it knows it's delivered. So in the future, it has less messages delivered. So this is going to be something that's really going to help our system scale. There are lots of queues you could use. In a multi-cloud environment, you're typically using Apache Kafka. If you are going to allow yourself to be locked into a single cloud, with AWS, you would use SQS, which we'll talk about soon. And I promise you, at some point, when we cover these things, we will get together and we will put together an architecture project. So the Amazon proprietary managed system to support queuing is the Simple Queue service. And they enable two types of queuing by default. A standard queue, which is messages come in and out as fast as you could process them. And that's generally going to give you the best performance. The alternative is something called the first in, first out queue, which is I send message 1 in, you take it out. I give you message 2, you take it out. I give you message 3. So that will generally give you lower performance. And here's the reason why. Message 1 may be a small message. Message 2 may be a big message. So by slowing it down into the way they're received sequentially may not be the best for performance. So just keep that in the back of your mind. In this example, you can kind of see what would go on with your CPU. If you were catching all these balls, for example, your CPU, would be running up really, really high. And maybe, the stock market opens and people process a lot of trades, right? So when that occurs, you might lose messages that the CPU might be too high. And then there's a period where nothing happens and the CPU gets real slow. And then a period where it gets crazy and the CPU goes up to near 100%, maxes out, and the computer crashes. We don't like this. But by draining that queue, pop it in, take it out, pop it in, take it out, we can slow it down. And because we slow it down, you can make the CPU on your database be much, much smoother. So instead of going anywhere from, say, 20% to 90%, we can keep it at 40%, which is going to enable us to scale. So here's what I think we should do. I will come back, answer some questions for a few minutes, if there are any, and then afterwards, we're going to go have fun and we're going to architect a high-performance, high-availability database. What can say about masking data in the database? So there's a lot that can be said. So the first thing I would say is, what's the use case? What are we trying to achieve and why? But there's lots of times when we may do masking of data. For example, we may have a lot of types of data that could potentially identify personally identifiable information. We may want to take that data and aggregate that data so we can run a research project on it, but remove that personally identifiable information. So that could be a type of data masking. You could also see that as data anonymization, but there's other types of masking in this concept as well. But generally speaking, that's why we do most types of masking, at least from an AI perspective or a big data perspective or a research type perspective. Chris, let's go to the next one. How does API architecture and API gateway is implemented and used in database? Please explain in details. So that's part of the overall application architecture. So the key is an API is going to be used anytime you want one application to talk to another application. I'm going to have APIs everywhere. So we're going to have APIs on the routers on that network because you're going to be pushing and pulling configurations from that network. We may have APIs with our IDS IPS systems to be able to push and change things that are going on there. We will have APIs that are used to connect our database, for example, to maybe the application servers. But we may have APIs to connect our database to other things or even other things to support the database like queues. So asking how does API architecture work? That's a 400-hour answer for an application architect. So I'm not an application architecture, but I'll give you a little bit of guidance on this in the meantime. But, realistically speaking, you can think of an API as kind of an endpoint to kind of create or do something with a database. Maybe for your CRUD operations, like your create, your read, your update, and your deleting data in the database. And, we can think of API gateways as a place to receive the API client requests and then route the request or direct the request to the appropriate backend service. The API gateway may manage the authentication and authorization of the request itself by integrating into an IAM system. And an API gateway can also limit the number of requests that are going to hit that API so it doesn't exceed the API's performance. Or in a DDoS attack, if you get way too many people trying to push to an API, you can throttle them to make sure not too many get there too fast. Now, as a backend service, we could be dealing with APIs to be performing database operations. It could be involved in, say, data handling, like receiving and processing data or returning results to the client via an API gateway. And in a manner like maybe a client sends a request to an API gateway. The API gateway would maybe route the request to, say, a backend service. The backend service then will interact with the database, and then the response might be sent back to the client through the API gateway. But that's just one use case. And APIs and API gateways and what they could be used could literally fill a 500-hour training session that an application architect would do. But I like the thinking. What is the advantages and disadvantages of vertical and horizontal scaling? Well, with vertical scaling, it's really simple to implement. You just put in a bigger server. And there's no code changes. There's no need to modify the application. There's nothing. Horizontal scaling, it depends. So if I've got a database like Apache Cassandra, that's designed to work on what's called commodity servers. Here's what commodity means. Cheap, couple $1,000 servers. So with Apache Cassandra, I just add a bunch of virtual machines. That's designed for horizontal scaling. But it all depends on the database itself. If I've got a database that can only write to one node, the master node, and I can't add additional horizontal scaling, I may have to make that master node huge vertically. And I might still have to scale out horizontally because scaling horizontally can handle the load by offloading more servers. And horizontally loading also improves my availability. If I've got 50 Apache Cassandra servers and 3 of them go out in an availability zone crash or a security event, I still have 47 more running. Whereas if I have just one big server and that goes down, so it's that. So horizontal scaling tends to remove single points of failure. And often horizontal scaling is cheaper than moving up into these big bad servers. But it also will make life more complex with horizontal scaling. And it makes data consistency a little harder with horizontal scaling. So it's about really looking at it and choosing the best option for what the use case is. But, that's good thinking. What is the time frame of sending, queuing, and receiving, inserting the data? So it depends on whether the systems are ready to receive the data or not. Having said that, with Amazon SQS, it's typically milliseconds to a few seconds to send to the queue and for the message to be drained. Now, several seconds is a lot. Milliseconds can be a lot too, but depending upon the application. But the choice is the queue makes sense. And how much stuff is what's coming in and what's the capability to receive it. So that milliseconds to seconds, that could be horrible or it could be nothing. So it's really based upon the application and what it needs. But generally speaking, with inserting or writing, that again is within milliseconds to a few seconds, depending upon the database loading configuration. But the latency, the service, the load, all of that's going to have a massive impact on what you're actually going to see. All right, so my team, read replicas, if you will, to keep it on the database theme, and we're going to go architect one together, have told me there's no new questions that have come in. So let's do this. If you're having a good time, please like the video. And if you're not a subscriber, please subscribe and hit the bell to be notified of new videos to help you in your career. If you haven't downloaded the labs or signed up for the free labs, go sign up. We have about 30 hours or so of live training that we're going to do. And I've got, 40 plus labs for you to do. So go do them too. So I want to make this a rich, full experience for you. And to know that you're awake, to know that you're alert, to know that you're oriented, please give me a hashtag. Hashtag SAAC03. SAA-C03. Sierra Alpha Alpha Dash Charlie 03. When I see that, we will start getting back into the content, and I'll just drink a little bit more of my alkaline water here. All right. So let's get back into the content here. I see you're all awake, alert, and oriented. So let's put some of the pieces together and how we can do this and how we can make it scale. Let me set up my whiteboard real quick. I've got pictures we professionally drew, but I don't think they're going to give you the same mileage as if we just go out there and we whiteboard it. So let's do this. Let's say this over here is our master database. And for traffic purpose, I'm going to show the way we do the traffic today. The traffic is coming in this way. So let's say we've got some web servers over here. Web servers. And then maybe we've got some app servers behind it. Oops, didn't mean to do that. Now let's say we've got a database over here. And this is your primary database server. And to make this look easier, we're going to be reading the data from the database over here, even though it would be another way, but just make it easy to understand. So somebody comes in from here, they hit the web server, they hit the application server, and they want to scale stuff to the database. So right now, this database is taking requests, and this database is requiring to requests. A million requests come in. It has to deal with the million requests and the million replies. And let's say there's also a million writes that come in. It has to do a million writes, a million requests for information or queries, and a million replies. The database is getting tired. It's exhausted. It's like a cat. It's like catching, balls every tenth of a second. It's going crazy. The CPU is high. So the first thing we can do is vertical scaling. So we were on a 64 core, and this is going to be a big database. Most of them don't use this, and 2 terabytes of DRAM. But I've worked with plenty of places that do. So now we're going to go from the 64 cores with 2 terabytes of DRAM. We're going to go vertical scale, and we're going to change this to a 128 core server, and we're going to change this to 4 terabytes of DRAM and a really good hard drive, and this thing is now happy. Now, guess what? It's not going to scale, because now that we have this, we're going to, hopefully the business is going to grow and more traffic's going to come in. So a lot of what this database is dealing with is stuff's coming in at it to be written, and all these requests are also coming in that need to be responded to. So now let's deal with the responding to. Let's say we've got 3 times the read load to the write load. So what do? We put 3 read replicas on here. If it's 4 times the read load to the write load, we use 4. So we'll call this an RR for read replica, RR for another read replica, and an RR for another read replica. Now, if things have gotten a lot better, the data gets written to the database, and the database writes the data to the database. And every time someone sends information to a read request, these read replicas say, got you covered, I got your 6, don't worry, master database, you don't have to do this. So you can see how the database is relaxing a little bit, because now it only has to deal with writes. And these guys, these read replicas, are doing all the reads. So we've made our system very interesting and very relaxed. Now we need to think about it. And now this database is the front end to, I don't know, give me a superstar that everybody wants to see what they do, or somebody with 50 million Instagram followers. So now a famous person tweets a photo of their super famous cat. This cat's worth like $1 billion. It's like the cool cat with 100 million Instagram followers, because everybody loves the cat in addition to the cat's owner. So now everybody's trying to request the same cat photo. They're coming from all over around the world to look at this cat photo. Well, now these read replicas are getting tired, right? So we'll put a cache over here, and we're going to use the cache. The cache is going to go along with the read replicas. So now we have Chris wants to look at a photo of Snoopy. I don't know. He hits the read replica. He goes to the cache that's not in the cache. Chris gets the read replica says, I've got a photo for Snoopy, or the data for Snoopy. The read replica sends it back. No big deal. That's the way it's supposed to. It's new traffic. Now everybody wants to go see the royalty cat. The first request goes through the app, hits the cache, hits one of the read replicas. The read replica responds, and guess what? Now the cache stored all the photo responds. Now the next 50 million people go to look at the cat that day, and it hits the cache, and the cache says, I got you covered. Read replicas, you don't have to work so hard, and it sends it back. So now we've integrated caching. We've integrated read replicas. So where do we put queuing in? So here's where the queuing is going to come in. And I want to so now we got that database, and it's happy. It's doing a great job. And now while we're at it, those millions, the 50 million cat photos are going out there for the people that requested the celebrity's cat. And now the celebrity says, I have a special t-shirt with my cat's one-on-one signed paw prints in it, and you get a photo of me with an autograph. Now what's going to happen? Well, now we got a lot of things. First, we got people coming in to see the photos of that thing, and the read replicas and the cache are responding to that. But everybody likes these photos, so now they want to order 1 million of these things. So now they stick 1 million orders coming over here, and they all sit over here in the cache. And then the cache sends them to the database as fast as the database can do it. And by doing so, if the database can only unload 500,000 of these, and this thing has 500,000 left, 0.5, and then while we're at it, another 2 million orders come in, which the database couldn't ever actually deal with. Now we've got I'm sorry, this isn't the cache. This to be the queue. Bear with me. It was the queue that's going to store the messages. So initially we had 1 million. We had 1 million requests coming into the cache. The cache, into the queue. So all these requests came into the queue. The queue sent it to the database as fast as it could. Only 500,000 of these were drained, so we have 500,000, but we've got 2 million orders for that special cat memorabilia or whatever it is, and the what do you call it? The autograph. So now they also sit in the queue. So why is this? So that one thing is when the CPU is too busy, we didn't lose those 2 million orders. So that's why organizations use this combination. Queuing reduces the write load on the system. Caching reduces the read load on the read replicas or the primary database if you don't have read replicas. And read replicas, they actually offload the read load from the master database. So I hope that made life a lot easier for you. And if that helped you understand scaling a database, give me a hashtag database architecture so that I know that it helped, because I hope that whiteboarding really did a lot to make it clear for you guys. So now we're going into some industrial grade NoSQL databases. So as I mentioned, I love DynamoDB. It's a beautiful database, but in 98% of organizations, it's not going to work because they're multi-cloud. So if we need a database that's going to work across clouds, it's going to move us into things like Apache Cassandra or MongoDB. Now, Amazon has a fully managed Apache Cassandra compatible database for you. And it enables you to run your Cassandra type workloads on AWS without managing your own Apache Cassandra servers. And if that's something you're looking for, then that's something that's going to work very well. Yorgos, it's good to see you here as well. It's going to help you in a lot of ways. So think of Keyspaces as an Amazon managed Apache Cassandra server. And it works and it's compatible with a Cassandra query language. And if you've got an Apache Cassandra workload and you want to move it to something that's fully managed in the AWS, that will work, and it will work really well. So I hope that makes sense. While we're talking about Keyspaces, it's a way for you to run and migrate to something that's not there. And by not having to provision your systems, you won't have to patch it. You won't have to manage the servers. So it does add some simplicity and elegance to you. It tends to scale well because it's fully managed. They typically scale up, scale down, whatever you need and when you actually need it. And, it's a high availability system that integrates beautifully into the AWS identity and access management systems for access control. You can put it in your VPC for that kind of thing for network isolation, or at least it supports the Amazon VPC for network isolation, and it gives you good encryption at rest and encryption standard. Now, when you're dealing with these Keyspaces or Apache Cassandra, you've got two options: on-demand mode and provision capacity mode. On-demand is it just sort of figures it out. I don't like leaving anything that matters up to figuring it out. Servers have a hard-coded IP address. You don't let them float around. You need to know where your applications are pointing. Networks are manually configured. And if you know your systems and you've got good capacity planning, use provision capacity because you'll know you'll get it when you need it. On demand, you will most likely get it when you need it. But you need to know your things before you do an architecture. So with an on-demand mode, you pay for the reads and writes you use. You don't specify it. And it just gives you and accommodates for you. But provision, you know what your information is, and you will specify it and you will get it. And if you find you're using too much, no big deal. So kind of hope that we're here. So next, where we're going to head, we're going to start talking about getting data and stuff to Amazon. How do you get your data there? Well, there's one way you could do it, which is what a storage gateway is. And what's a storage gateway? So a storage gateway is a virtual machine that is Amazon calls an appliance. And basically, it's a pre-made virtual machine that'll either be used with Microsoft's Hyper-V, the Windows server native hypervisor, or VMware, which is what most organizations actually use as their enterprise-wide hypervisor. And it's kind of great. So you mount the server in your data center. You've got your, say, direct connection or your VPN over to AWS, and it will just copy your data over for you. So If you got a hybrid cloud and you want to keep two sets of data in two places, the storage gateway is awesome. So if you want to migrate to just the AWS cloud, the storage gateway is a great way to do it. Now, when it comes to storage gateways, there's really three kinds. There's what's called the volume gateway, a tape gateway, and a file gateway. And we're going to talk about all three. We'll start with the file gateway. That's going to be an appliance that, meaning virtual machine, that's basically a file server, and it will just connect it to the cloud. So it can be a Windows file server that you would use, and you would use the server message block protocol, or you can mount to it via server message block for Windows, or it also supports NFS for Linux. So you got a bunch of Linux and Unix systems, you connect to this file server via NFS, file share, and then it just copies your data asynchronously to S3, and it's stored as an object on S3. I mean, that's really cool. Have everything you want, make it your main file server, and you have it locally for the best performance, and it's all archived in the AWS cloud. So it's a really great option. And when the files become objects on S3, they're going to be encrypted with Amazon server-side encryption, so you'll get encryption. Here's another way, you can kind of look at it. Let's say you've got this environment where you've got this file gateway, storage gateway, whatever kind of thing we're talking about here. Graphic still applies. You take your application servers or your users, you mount that storage gateway as if it's a file server. Over your direct connect, it puts us to Amazon, stores it on object storage or S3. And then as we talked about yesterday, it might be something you need to access frequently for a while, so you keep it on standard S3. Then you might not need it very often, so you put it on S3 and frequent access, where you pay less, but you pay a retrieval fee. And then you may not almost ever need it, so you stick it on Amazon Glacier, where it's real cheap to store, and then you pay a retrieval fee to get it, and you have to wait a period of time to get it. So that's called, life cycle management of storage, and especially in the cloud, where storage is much more expensive than, say, in the data center, we have to work really hard to keep our costs low. So I'll talk about an AWS file gateway. And that's basically very similar to what we're talking about as well. It's a file server. It's made to look and feel like traditional storage. And basically, it's a file interface. So if you've got a file or an object in S3, and you've got this file gateway, in the data center, you can pull it across that gateway, and it'll feel like a traditional file storage, even if it's coming from S3. The file gateway can also cache the information. So you've got this file gateway, you've got some information stored in S3. Let's say it's, it's a photo that everybody wants to see. What's a photo that everybody wants to see these days? Honestly, I don't even know. So let's say there's a celebrity cat out there that plays bingo, I don't know, and it wins bingo games. So if everybody wanted to see the celebrity cat, and we had a photo of the celebrity cat in AWS, we don't want to go across that direct connection every time and reach that celebrity cat. But if we had this file gateway in our campus, and we all mount and connect to the file gateway, the first person gets a photo of the celebrity cat that's playing bingo. The second person doesn't have to go across your direct connection to AWS S3 to pull it because it's locally cached. They just get it from the local server because somebody else wanted it. So that's one of those cool things to think about with regards to file gateways. And one really good thing about object storage in AWS or S3, it's very durable. I mean, they've got a really good backup scenario. So the chances of your data being lost on AWS are slim to none. That does not mean you shouldn't use a good offsite backup routine, but it means the data on AWS S3 is very durable. So good chance that you'll receive your data and they won't lose it for you. And because you're pulling things off of AWS from AWS, it's going to connect very nicely to things like AWS Backup, AWS Lambda, AWS CloudWatch, that kind of thing. Although, really think about this. If you're going to back up your data or do disaster recovery from AWS, you probably should back it up to maybe Azure or Google or somebody else, not AWS. So just think about that. The point of disaster recovery is what happens when all the systems go down. So don't put them all your eggs in the same basket and expect the same people to go that what could have potentially went down on any cloud to be your disaster recovery people. So file gateways support encryption in transit, meaning between you and the cloud provider, and at rest, meaning when it's stored. They integrate beautifully with the identity access management part of AWS. And you can set up the same kind of folder and file permissions that you could in any other file server, because it's going to act like a pseudo file server pulling objects from S3. If you automatically change a file, it'll upload it to S3, so your data gets synchronized and consistent across two places. So AWS File Gateway, it is beautiful for backup and restore, meaning have all your data stuff in your data center, have it copied over AWS in two places all the time. So that's a great thing. You could use it as a hybrid cloud. You've got some of your users in the data center, some of the users in the cloud. You could use it for a hybrid cloud workflow where 50% of your data is on the cloud and 50% is in your data center, and you want to be able to pull what you need to. You want to archive your data. This is a good, easy to use solution. Disaster recovery, yeah. What if you basically had your entire data center and used AWS's disaster recovery by constantly backing up your data in virtual machines to Amazon? So file gateways are great. Basically, to set them up, you deploy the file gateway, that virtual machine. You either put it on your VMware ESI systems, Microsoft Hyper-V, that kind of thing. You connect your gateway to the AWS account that you have and configure your file shares. You know, if you're dealing with Linux systems, you create an NFS file share. If you're dealing with Windows, you create an SMB file share, the server message block protocol, map them to S3. And then when the on-premises applications need to access the file shares using standard file sharing protocols, because they don't see it as object storage, they will see it as file storage because it's a gateway. And a gateway generally takes one type of thing and connects it to something else. And you've got really good data management with this file gateway as well. The gateway uploads the files to S3, stored as objects, and then it even manages the metadata and makes sure you've got good data integrity. So you can think of it this way. And you can also have, you know, a gateway literally in the cloud, which you could connect to storage gateway service. You're connecting to the storage gateway service in the cloud. So you put this virtual machine in your data center. You've got this HTTPS type connection, which is, think TLS encryption. And you can store your information on the cloud. So very good situation. So now we're going to talk about a volume gateway. And a volume gateway is a service within a storage gateway that provides cloud backed up storage volumes to your on-premise. So you can attach to these volumes on your on-premise servers with something, say, like iSCSI, if you're familiar with the iSCSI way that's to attach to storage. It's basically the SCSI protocol that's encapsulated into IP packets. And this enables you to leverage the scalability and durability of your AWS cloud storage and still keep good local performance. And as I mentioned, it does cache volumes. So you can store your primary data in S3 and maintain access to frequently accessed information locally in a cache. You might use it to reduce the scale of your on-premise storage and still giving you decent performance to data that's going to be stored on the cloud because of the caching. Here's typically the way I had always thought of these when we drew this out. You've got your computers, your users are going to connect to this thing, and they're going to be pushing and pulling information across AWS. Those servers themselves are going to be connecting to the application gateway over here. Here's the gateway, and here's your systems. And it's that iSCSI protocol that's going to be used as like a virtual storage area network, if you will, access. So that's really what we're talking about over here. Of course, that was volume gateway cache mode. Now we're going to talk about volume gateway stored mode. So stored mode is where you're going to take your primary data and keep it locally. And that's going to asynchronously push it to the cloud. So When we talked about cache mode, that was assuming that the predominance of your data was sitting in S3. But if your data is predominantly local, but you want to back it up to the cloud, this is where your VM gateway goes into stored mode. And this is going to be ideal for applications that require low latency access to maybe an entire data set, because the latency is going to be lowest in your environment, lowest in the data center. That's why data center performance is always going to be the best. But sometimes we need the scalability. Lots of times we need the business agility of the public cloud. So local storage performance, back it up somewhere else. Keep going to the back thing. So it's going to look very similar to what you just saw. The systems are going to connect to the users will connect to the application servers. They'll be connecting to this VM gateway, but it's going to be in stored mode, and it'll still push the content to S3. But the point is, our local storage is here, and this is where we're going to get high performance access to locally, and it's still going to. So you're going to see this is going to be our high performance locally, and then it's going to store backups of this information in the AWS cloud. So that volume gateway we just talked about is going to be perfect for that hybrid cloud storage. The fact that you can connect to it via the iSCSI interface realistically means that your systems are going to have no problem to it. You deal with a Red Hat system, it'll mount iSCSI. You deal with an Ubuntu system, it's going to mount iSCSI. It's just a standard way to access storage over the Internet Protocol because it's based on the SCSI protocol. And this is excellent just for data backup, data protection, disaster recovery. And if you think about it, it's going to scale. Because when you have in your data center, you can just add extra to your storage area network. And the cloud's just going to grow with you. So it's not like you're dealing with, where's my redundant data center, redundant backup environment? Does it have enough hard drives? You don't have to worry about that. And when your data is stored, it's encrypted. And this way you've got low latency and you've got really good backups. This is a great environment for hypercloud. The next kind of storage gateway we're going to talk about is something called the tape gateway. So I don't know how many of you are familiar with tape backups. You've got a person swapping tapes, and then you take the tapes when you're done with your tapes, and you typically ship them off-site. So then you need some high security shipping, and then you got to store those tapes in a high security building. That's typically, a tape backup environment. So the AWS tape gateway is going to do things just a little bit different. And it's going to work with an organization that's got a good tape backup infrastructure. But at the same time, they don't feel like swapping tapes, shipping tapes, storing tapes. So, this is a great environment. So a tape gateway enables an organization to use their tape interface, and they create these virtual tapes. And these virtual tapes are stored on Amazon. So, I hope that kind of makes sense. So we uses the concept of these virtual tape libraries. So they emulate the physical tape. So all the backup applications a business has, where it's looking for a certain set of things, it's still going to work, but it'll work on a virtual tape versus a physical tape. So the same backup software works. In this way, you get the benefit of being able to put your backups on the cloud, not have to think about managing of these tapes and when the tapes go bad and how you destroy the tapes when the tapes go bad. You're just sticking it in AWS, and AWS is a virtual tape for you. So very scalable, great environment, fairly cost efficient. Because, all these tape media, tape drives, tape this, tape that can somewhat get a bit complicated, and sometimes it can get expensive. But when it comes to cloud computing, what looks cheaper might be more expensive. So you really need to understand all of it before you actually build a business case. And of course, it's on S3, and we talked about S3 having that 11 nines availability, meaning 99 and the 99 for 9 decimal places pointed after the 99%. So fairly durable data. The data is going to be encryption because it's also going to have access to the AWS Identity and Access Management Systems, which of course could be federated or pulling into the organization's Active Directories like they usually will be. And the way the tapes come in is it typically comes into the tape gateway, and then it gets stored in S3, and then it gets moved into Glacier where you're going to have your cheapest performance, because chances are you're not going back to your tapes. You want it to be in the lowest cost storage. And if you do go back to your tapes, it's because a catastrophe has occurred. So tape gateways, backup on archival purposes, disaster recovery. Tape gateways are also good because if you're in a regulated industry and you actually have to store your information somewhere else for a long period of time, it's, a great way to archive your systems. Because if you're a hospital and you lose patient medical records, you got a problem. If you're a bank and you accidentally lose financial transactions, you've got a problem. So think about that. And, this way you're not dealing with tape. So how does this get set up and used? So you deploy the gateway. Basically speaking, you install the tape gateway virtual machine on your VMware, your Microsoft Hyper-V environment. You can configure that gateway to connect to your AWS account. You create your virtual tapes. You integrate with your backup software, so you configure your existing backup software to use the virtual tape library presented by the gateway. And you do your backups. And then you archive it on Glacier from S3. And if you need it, you restore your data. I think we've probably gone on for more than 20 minutes, Chris. So maybe we will stop here, and then we'll come back and talk about some other options. Volume Gateway Store Mode. Data is local and high performance local. A store backup to AWS Cloud. Can you please detail some additional use cases? Access storage over the internet. Cloud and backup in DR. AAE, I'm not 100% sure that I understand your question. So let's talk about some use cases, because the data is local. And this way you can get some local high performance and still back it up to AWS. So where would you use this? Well, if I have an environment where I want good disaster recovery, I want my local data backed up somewhere else, and backing it up to a cloud provider that's 1,000 miles away is perfect for business continuity in case we have a local hardware failure. If I want to have a hybrid cloud environment, it's perfect to keep my data synchronized. If I want to move to the AWS cloud, it's going to be pretty great because you can work off of your local high performance setup, and it's going to just asynchronously copy it to the cloud. So if I've got an environment where I've got under high regulatory compliance, so medical, publicly traded companies, banking, highly regulated environments, this is going to be an environment where we want offsite backups. And think about data synchronization. You can run an environment where you've got a hybrid cloud, and what happens if your data center fails? You want the cloud provider to be able to take over. And if the cloud provider fails, you want your data center to be taken over. So there's lots of good reasons to keep your data synchronized in two places. Hope that answers your question. If we want to store the tape backup, how long does it take? George, I honestly don't know, because I've never restored a tape backup because I don't work in operations. But we will talk about some extremely good ways to do disaster recovery and ways to speed it up versus slow it down. And it's also going to be based upon how much data the organization actually has as to how long it's going to take to reconstitute that data. And, if we're going to do it from a storage gateway, for example, it typically takes a few hours. But that's going to be the size, that's going to be dependent upon the size of our data and our network connections. Restoring data from a storage gateway to tape backup, again, is usually a few hours, but it's going to be really dependent upon how much data you have and the speed that you actually have to get your data from point A to point B. Oh, that's a good question, Derek. When would you use a tape gateway for backup when you can simply make an image and store the environment? So if you have an existing tape backup infrastructure, and that's realistically speaking what the organization is used to, it's the way they've done everything, and that's the only backup strategy they have. Sometimes changing an organization's entire backup strategy is going to take a while. It's going to take a brand new architecture, which means it's going to have to go through approval phases, and the executives are going to have to buy in on it, and the stakeholders are going to have to go through that. And it could take 6 to 12 months to do that, just to design the new storage and backup architecture and get it approved from all the levels in the business. So this is quick and easy. In real pragmatic reality, if I've got the ability to make an image of every single server I have and keep copies of those images on the cloud, and I could have a Terraform infrastructure as code script to basically bring up those things, and I've got exact copies of my machines, especially if I kept my databases synchronized, for organizations that can invest in that, it's going to be a much better solution than tapes. But sometimes we deal with people that have been doing something for a long period of time, and they don't have the capability or the wherewithal to make the change, or the sophistication to make the change, or the budget to make the change. That's when you use the technology they have. But Derek, I'm glad you thought of this, because it means you're thinking, why would I use this kind of clunky old thing when I have access to something better? Good point there. All right. Did you all like working through the database and kind of mapping it out and playing with it alive? I hope so. Let me know if you did in the chat box. So we'll get back to the content. If you've not downloaded the free labs or signed up for the free labs, please do so. My team will drop a link for that in the chat box as well as in the description. We're here for certifications, and we do lots of free certifications on our YouTube channels, and I can tell you, it saddens me when I get somebody with all these certifications in someone else's job, and sometimes I see a beautiful resume with exactly the right certifications, and it really makes me think very differently of them when I read the resume. So I want you to know this, so you know how to plan certifications for your career. So go get that free certification guide. It's in the chat box and the description. So we're now going to talk about, the AWS Snowball. And one of the ways you can typically get information to the cloud provider is basically by putting it on a hard drive and shipping it to them. So AWS offers these little virtual file servers they send to you. And basically it's this ruggedized container, and it's got a specialty computer in there with a 10 gigabit Ethernet port. And what you do is you plug in this little mini ruggedized file server to your network. You can put, say 80 terabytes on it. Well, it's technically 72 after you format it, but it's 80 terabytes of raw storage. You copy your information into the Snowball, which is just a file server, and then you ship it back to AWS. They ship you a server, you pop your information on the server, and you ship it back. And when it gets to AWS, what do? They store it in object storage. So you request the Snowball, they deliver the Snowball. The Snowball is just the file server. You load your data on the file server. AWS picks up the file server, sticks it on S3 object storage, and then you pull it off of object storage and do whatever you want with it. I am not sure if they have canceled the Snowmobile or not. I am not sure, but I want to give it to you anyway because it may still show up on an exam. So AWS also had this concept of a Snowmobile. What's a Snowmobile? Basically, it's a data center that gets shipped to you. You copy your information to the data center, and they drive the data center back to AWS. So it's a data center that can store upwards of 100 petabytes of data. So AWS basically takes a tractor trailer. They drive this thing over to you. You plug into it to your network. You copy your information, and they drive it back to AWS. They copy your information onto AWS S3, and then you pull your data off. That's another option. Another option we have is AWS DataSync. And AWS DataSync is a managed service that's going to simplify and automate moving data between, say, your on-premises environments and your AWS storage service. It can sync your data between multiple different AWS storage services. And it's designed for large-scale data transfers to do it in a secure and an efficient manner. And AWS DataSync provides for automated data transfers. So it reduces the need of manually intervening and writing scripts to push your data. It handles the complexities of data transfer, so you might need to tune the network for it. You may have to validate the data. There may be some error problems and need to do some error handling. So it does all of that. And it supports lots of different storage devices. So S3, or storage services you could call it. So object storage, elastic file storage, or network file storage, FSX Windows for file server, so Windows file storage, FSX for Lustre, which is high performance file storage, Amazon FXS for OpenZFS, it's another file system. And that's the key thing to remember. So it really works with all kinds of different storage and storage protocols. It'll integrate with the AWS key management system. So you're going to have your encryption, and it'll also integrate with the AWS Identity and Access Management Console to control, who can access your resources. So identity and access management is who are you, what are you allowed to do, and what have you done. So keep that in mind. It'll work with data validation and integrity checking, because it's going to perform data integrity checks to ensure that the data transferred is actually what you started with as the source. So that's going to be quite good. And it's going to verify data during the transfer process to maintain its accuracy. You can schedule it. You can schedule data transfers to run at a specific time of day. And why might you do that? So let's say you want to transfer data. During the day when the network is busy, you might not want to do that. But maybe the computer systems are getting minimal use in the evening, like at 2 o'clock in the morning, and that's when you want to send it. So that's why you would schedule these types of things. AWS DataSync can also do data filtering. So maybe you don't want to back up certain things. It can enable you to do that as well. Now, as we're talking migrations, let's talk about another service called the AWS Migration Hub. And that's going to be a service that provides a single location for you to track the progress of application migrations across many AWS and partner solutions. So it's going to help you manage the migration process, give you visibility into it. Now, this is not an architect tool. This is going to be at the operations level, at the time when you're actually doing the work. But keep that in the back of your mind. If the organization chooses to use the AWS Migration Hub as one of their tools, it'll give them a dashboard about the status and progress of the migration projects. And this is going to help streamline, the management and migrations of things, because it gives you a unified view. There's lots of tools project managers can use in large-scale migrations, etc. But, this is an AWS tool. And it's going to integrate with a lot of the other AWS migration tools. So AWS has an application migration service to kind of help you move applications. It has a database migration service. If you were going to go off of, say, your Oracle database and wanted to use one of the AWS databases, of course, you could just take a virtual image of your server and move it to the cloud. And AWS DataSync and lots of third-party tools. So you could use AWS Migration Hub in the discovery and planning phase, and maybe by looking at the applications. For example, you can group your applications in an environment that enable you to track the migration, say, progress of an entire application rather than certain individual resources, to get more of a holistic view, if you will. The service will provide metrics and reports on migration activities, including details like the number of servers migrated, the amount of data transferred, errors, warnings, that kind of thing. It'll give you information on progress tracking. So think about it as a tool to kind of help you, this migration hub, to figure out what's going on. And it can also help with some automation and orchestration, because it will support automation and orchestration of migration tasks. So some of those manual things can reduce manual effort as well. Now, next is the AWS Transfer Family. This is a fully managed service from Amazon Web Services that will enable you to transfer your files back and forth to AWS storage. It'll support numerous protocols, making it pretty easy to share and integrate data. So you can use, say, secure FTP. You could use, say, FTTPS, which is FTTP with SSL/TLS encryption. It'll also work the transfer family with old school, non-encrypted FTP. And the AWS Transfer Family will integrate with S3 or object storage, the AWS Elastic File System, which is the AWS managed version of the network file system. You can use it to help with data migration because it can help get your data to the cloud. You can use it to basically do data sharing. So what I mean by data sharing, you may have your business that needs to share data with multiple other businesses, so it can assist with that. And it could be used for backup and restore. I'm going to cover Amazon Work Documents. You probably wouldn't see it in an exam, but you never know what you're going to see, so I'd rather just cover it. Amazon had their version of, say, Google Office or Dropbox, and they called it Amazon Work Docs. It was like a secure content storage and collaboration service, easy way to do document and editing. It was simple and affordable, and you could access it with a web browser or client software. Worked with Windows and Mac clients, so something to think about, something they have. All right, now we're going to get into some fun stuff. We're going to get into compute. The actual computational part of everything we do in cloud computing. So this is where the fun is. And we're going to first start with virtual machines. And I'm going to make sure that you understand virtual machines long before we talk about EC2, because if you don't, you're just not going to know where to begin. So first, let me logically show you what a virtual machine is. We'll map it out architecturally, and then I'm going to take you to our data center, and I'm going to show you an actual physical server, and I'll show you the hypervisor and basically what is an EC2 instance from the inside out. Because if you don't know what it is, you're not going to be able to really understand what it is if you have to design it. So let's say let's map this out architecturally, and then we'll go to our data center. So let's say this is your actual physical server. So that's the server you buy from Dell or IBM or HP or anybody else. That's your server. Now let's say this is a big, powerful server. It's using AMD's EPYC processors, which are the fastest processors in the world. Let's say it's got 256 cores. And let's say it's got 6 terabytes of DRAM. And this will be about $300,000 for a server like this. Relatively inexpensive compared to the cost of running the server on the cloud. Now, most applications don't use 256 physical cores or 512 virtual cores. They don't. In fact, many applications won't even use a full core. So one of the things that happened many years ago was we said, well, our data centers only have so much power, and we don't have anywhere close to enough electric to even deal with the the things that we need to deal with, let alone anything else in the electric infrastructure. But that's neither here nor there. So we could buy 50 servers that all have, say, 4 cores each, and they all use the same amount of electricity, and they all take up rack space. Or we could buy one server with 256 cores and chop it down into multiple smaller servers. And this is how all your systems are on the cloud. So what happens is you put what's called a hypervisor here. And this will be a type 1 hypervisor. And what the hypervisor does, and there's no operating system here, it's the hypervisor, it's like a mini operating system. It will enable you to create little mini servers off of this main server. And by doing so, I could create an additional server with 4 cores, and 8 gigs of RAM, I could create another server with 32 cores. So it enables you to create multiple virtual machines. So here's the way these virtual machines are. Well, let's say this is a 16-core virtual machine, and they're logical cores, not physical cores. And let's say this has got 64 gigs of DRAM. What it does is it takes those resources out of this. Now, this virtual machine will have its own OS, its own applications, and whatever the application dependencies are. And I can have many of these things. And, you know, what I could do is I actually get what's called logical cores because these cores split our hyperthread. So if I have 256 cores, each virtual machine is a virtual core, which is technically a half of a core, although it can perform almost as well as a full core under certain circumstances. So out of this, if I've got 512 physical cores, and there's a reason I want you to understand this, if each one has 16 cores, I would do 512 divided by 16, which could mean I could run 32 servers on this system. Now, do you see this? This first server, this could actually be customer A, and this could actually be customer B, and this could be coming from customer C, and this could be customer D, all on the same physical server. And in some ultra high security environments, you will not be able to use a server like this in the cloud. But by default, this is what you're getting. Your systems are on the same system as other customers, and they're all sitting on that virtual machine. Now, one of the things that cloud providers generally do, and internet service providers typically do, is they work on this statistical calculation that this system has 16 cores, and this system has 16 cores, and this system has 16 cores, and this system does. And what's the likelihood that all 4 of these virtual machines are going to use all their CPU performance and all their DRAM performance at the same time? Not a lot. So while the cloud provider could technically sell 32 actual servers at capacity, they may sell 65 or 70 servers on here. And that's called oversubscription. And they may do that because they know that most users, statistically speaking, won't use full capacity at the same time. So if you ever hear about cloud computing having bursty performance, it's because sometimes these systems get busy because they typically sell more than they actually have. And this is common of your internet service provider. It's normal. It's part of their normal business model. And even airlines do it because they know a lot of people won't show up to a flight. So they sell maybe 10 or 20% more seats than the plane can handle. And then it usually works out. And if not, they're like, who wants to get to leave the plane and get money? So that's the way this works. So now I still want you to understand a little more of what this looks like. So let me bring you to my data center. In my house, which is my data center, I've got an OpenStack cloud. I've got a VMware cloud. We've got all kinds of tech around here. But here is a traditional server with a hypervisor. This is a Dell. It's actually a workstation, but it uses the same processors that the AWS i3 instances use. They're all this Xeon E5 2670 V3. Note that this system has 24 physical cores. And you can see up in the top of this how much resources are free on the system because we've got 24 cores operating at 2.3 gigahertz. We've got a total of 56 gigahertz, so to speak, or 55, 56 gigahertz to use. We've got 128 gigs of memory. Some of it's being used by the hypervisor, and you can see that, 80% of the server storage is used. Now, I want you to see that. You can see this system's not being used. So in the data center, we're going to create a virtual machine. What's it going to look like? Well, we'd create it. We would tell it about the virtual machine we need. Let's give it a name. I'll call it Cindy the cat. I have a cat, Cindy. She likes to unplug servers. Guest operating systems, let's say it would be Linux. Guest OS version, we would pick the operating system version. Red Hat Enterprise Linux, probably what I would be using in a business case. We can set it up for standard, and then look what we can choose. The first thing I want you to see is I now have the ability to delegate 48 processors cores. Wait, we only have 24 in the server. So when you get a virtual machine on the cloud, it is a virtual CPU, which is meaning is it's not a full CPU core. So understand, 16 core virtual CPU in the cloud is not going to perform as good as 16 physical cores in the data center, which is 32 virtual cores. So you're going to have to adjust your sizing accordingly. But the way this would work is you would get a virtual machine and determine how many cores your application needs. Let's say in this case it's 4. You would look at how much DRAM your application needs. Let's say it needs 16 gigs. You would tell it how much of the hard drive that it needs to take, and that's going to take it from the internal storage here, at least in this environment. You would give it a boot device to boot up, which would be, say, Ubuntu desktop, and then I would just build the system, and I'll let you see how the system boots up, and then I'll cancel this because you don't need to see me install Ubuntu. But here we've got the virtual machine, and guess what you're going to see? It's going to boot up just like any other computer. I'll let you see that, you can see what it actually feels like. And now you can see that it's going to load up. I'm going to stop it here, but wow, that just looked just like a standard server, right? It's a server inside of a server, and that is the basis of cloud computing. Now, we don't need to see the rest of this occur, but I wanted you to get that, because if you didn't understand what that was, anything else that we would actually show you wouldn't make sense. So I hope that actually worked. Made life easier for people. So I really want you to get a good experience here. If you understood that, and now you know what a virtual machine is, give me a hashtag VM. And I don't like acronyms, but I know everybody's not going to want to type a lot. So give me a hashtag VM. And then I know that you understood that, and it helped. All right, so now let's talk about the AWS branded virtual machine. On AWS, you still have the same virtual machines that we have had since 1999, that VMware invented. So here's what's different. AWS made a new name for it. They call it the Elastic Compute Cloud, otherwise known as EC2. If you talk to an end client, it's the virtual machine. And how do you determine what size you need of virtual machines? It's the same way you've done it for the last 2 decades. How many CPU cores do you need? What are the frequency of those cores that you need in terms of, say, single core performance or multi-core performance? Do you need a graphics processor in it? Do you need accelerators for parallel computing? How much DRAM do you need in it? What kind of storage capacity and performance do you need? What kind of network performance? Now, AWS has these little marketing-friendly little terms that you can look at, and they size their instances by marketing names. Like an i3 is considered, I don't know why when we made this, it was considered high-speed storage. Now it's considered general compute. But the point is they come up with a name. Typically speaking, a G-series virtual machine has a GPU in it. They have some things that are memory optimized. I'm going to give you the reality. None of that matters. What matters is your CPU performance, your DRAM, your networking. So what you're going to need to look is the CPU cores you need, the DRAM performance that you need. Excuse me one second. All right, apologies. Something made me sneeze and cough. So when we get our virtual machines on AWS, they're either going to be Linux virtual machines, Windows virtual machines. We're going to go to the marketplace and say we need good security, and we're going to go get a Cisco firewall or a Palo Alto firewall. And they also do support Mac OS virtual machines. Now, the way these Mac OS virtual machines are is they literally run on the data centers. They've got racks and racks of little mini Mac minis. But why would you use an Apple virtual machine? Well, you might use it if you're a developer. You need to compile code for a Mac, and you don't have a Mac. So, there's times in a place where you might want to use an AWS virtual machine, but they get very expensive, those Mac virtual machines. So when you get a virtual machine, you've got multiple options. You can take the virtual machine you have in your data center, that file for it, convert it to the Amazon file, and just launch it directly in the AWS cloud. If you had VMware or Nutanix, If you could run VMware on a server in the cloud and just move your virtual machine as is and use the same VMware tools to do it with a bare metal server. You could also just launch an Amazon pre-made virtual machine. So launch a Red Hat 8.0 Red Hat Enterprise Linux H.0 server. Boom. Click a button and it's launched. So they're pre-made. So when we deal with Amazon, we're going to have this concept of an Amazon machine image. What is it? It's the Amazon branded name of a virtual machine image. So VMware had their images. Everybody has their images. So when you deal with an Amazon machine image, it's going to need a storage volume. Think EBS, where you're going to store your information. And we can get these Amazon machine images from a lot of places. There'll be lots of systems that are going to be pre-built by AWS for a variety of needs. Now, we might need an extra high-performance reverse proxy and get one from, say, F5. We may want to stake DNS servers in multiple clouds, so we get them from all the clouds marketplaces. We might need a high-security appliance that we get from Cisco or Palo Alto or Fortinet, and enterprise security we will be. Typically speaking, getting one of those things. We might need an IDS IPS system, and we're going to get it for something like that. So there's going to be pre-built machines in the AWS marketplace for a tremendous number of business uses. You'll be getting them. Or you'll just take one of your systems that you have, say a VMware virtual machine, copy it over, and turn it into the AWS format. You upload your virtual server. Now, what are the components of an Amazon virtual machine image? An operating system, launch permissions, and a block device mapping that's going to specify the storage volumes to attach to the system. So, OS, permission, and storage, like any other virtual machine in the entire world. One of the cool things is you can take your machine image and you can copy it to a different region. You can create a snapshot or a quick mini backup of the image, and you can use this for backup, disaster recovery, and there you go. You got lots of these options. Excuse me. So let's talk about automating the first boot on your virtual machine. So think of it this way. When you just launch a basic virtual machine, it's not going to have any software on it. So it's going to have nothing other than Linux. So we have the opportunity to launch what's called a bootstrap script. And what is a bootstrap script? It's a simple script to install applications, manage your software, patch the operating system, and very simple. It could be a bash shell script, a Windows parallel script. It could be an Ubuntu system, and in the location you can do a sudo apt-get update and update the system, that kind of thing, and you could specify it. You could have your system install maybe an Apache web server as it boots up. And so, just have it set up. So patch the operating system, install the Apache web server, do this, and come up. So we can automate the boot very easily. So if you think about creating an input script to make the system the way it would be, and businesses have been doing this stuff for decades and automating, Windows rollouts when they install the systems to their users, for example. We can automate systems with, you can use the AWS Systems Manager and use run command or an AWS automation documents to execute commands remotely on a system. When you use infrastructure as code, which means Terraform because everybody's multi-cloud, or the AWS CloudFormation, if you're only going to deal with AWS, and you can define your instance configurations, the bootstrap scripts within your CloudFormation template or Terraform template. And that way you could launch like 10,000 virtual machines in a matter of minutes. And that's one of the reasons infrastructure as code is so great. You could use it with, say, AWS OpWorks and use some kind of Chef or a Puppet configuration to automate software set up in your virtual machines. So there's lots of options. Now, when you get your systems, these virtual machines from the cloud, basically have a couple ways you can purchase them on demand. So occasionally you'll hear people say you don't need to do capacity planning on the cloud, it'll work. Well, that's true if you don't care what it costs. And actually it's not true, because even if you don't do capacity planning, it won't scale when you need it and it won't perform right. But if you know what you need, you can purchase it. If you know you're going to be in a house for 3 years and the landlord would give you a 40% discount because you give them a 3-year lease, not that they would, you might basically say, I know I'm going to be here. If you didn't know how long you were going to stay in a city, and it could be 1 day or 1 week or 1 month, you'd stay in a hotel. So that's really what we're talking about here. When you purchase your virtual machines, you need to know your utilization, how much you're going to need, and for how long you're going to need them. So on demand, think of it as real expensive. You have no idea what your needs are, and you're going to pay out the nose for them. That's an on-demand instance. By comparison, reserved is, please give me a discount on my 3-year rent or my 1-year rent. So if you know what your needs are and you go to any cloud provider and you reserve them ahead of the time, they're getting guaranteed a certain amount of revenue from you, and they're willing to give you a discount. And it could be a relatively good discount. And, there's 2 kinds of reserved instances. There's a standard reserved instance for the most part. Actually, there's a few kinds. And that's going to give you the highest savings, but you've got limited flexibility. There's also something called the convertible reserved instance, which gives you less savings, but you can change your instance type, operating system tenancy during the term. So with anything else, if you need the ability to control stuff, they charge you more. So think about that. So we talked about on-demand. Here's when on-demand is good. When you don't know. You're a brand new startup. You have no idea what your needs are. On-demand instance. A big business moves from their data center to their cloud, and they've got really good cloud architects. And those cloud architects know the system's utilization. They've done all the math, and they're going to the cloud. And they're not just certified. They understand business. They understand architecture. They get the concept. Go to the cloud. Reserve it for 3 years. Next, spot instance, or if you want to auto scale, that's going to be on-demand instances. But, that's a great thing. The next thing is something called the spot instance. A spot instance is maybe one of the most terrifying things you can think about, or a preemptible instance on other clouds, but in some cases it's really great. So these cloud providers have a whole lot of excess capacity. There was a movie, I think it was called Field of Dreams, where they said, build it and they will come. Well, that's generally the cloud provider's motto. Let's build it and hopefully someone will come. So they've got all this excess capacity, lots of the time that's sitting around doing nothing. So you can purchase a spot instance, which basically says you agree to bid in an auction environment for a certain amount of compute time at a certain price. And as long as nobody's using it, it works. But then somebody bids a little more than you, and within 2 minutes you get shut down. So let's think about this. If you have a batch job to do that requires a huge amount of computer processing for maybe 12 hours, and you don't care if it starts and stops a few times, spot instances are the way to go. If this is your business website and you're in e-commerce and you're going to get shut down during the day, this is not the way to go. So I hope that makes sense. So next. Normal tenancy of one of these servers is as follows. You are shared with a whole bunch of other people on the same business. Now you have a top secret, super important thing. You don't want somebody to be on that same other server and have the potential for a hypervisor attack and get into your virtual machine. It's rare, but it can happen. But if you've got mission critical security, you may need to be on a different server than other people. And that's where you start getting into different types of tenancy. So we'll talk about a dedicated host. The dedicated hosts are realistically going to be in an environment if you need, say, compliance requirements, and you need to use a per socket or per core or per virtual machine software license. And you can think of it that way. So basically you can think of it as a system that's yours, like in a data center. Now the alternative is a dedicated instance. And that's where you basically run all your virtual machines and only your virtual machines on the single hardware. So you've got host level isolation as well as hypervisor level isolation. So it's going to give you a lot more security should you need it. You can also reserve capacity. And you've got this concept of capacity reservations. And that will allow you to reserve capacity for one of your virtual machines in a specific availability zone for any duration, making sure you've got the capacity necessary when you need it without having a big long-term commitment. And there's this new concept of capacity blocks, and it's new for 2024, and it's specifically designed to reserve clusters of GPU instances if you need basically a workload that requires a lot of high-performance compute. I want to talk about that tenancy a little more. Probably see you could see questions on this on your exam, but it's really important to understand from a security perspective. Shared tenancy. Multiple customers on your same virtual machine. So if you think about a hypervisor attack, that's how you could go from one virtual machine to another. With a dedicated instance, it is single tenant hardware, which means if I have my business and I have a dedicated instance, only my virtual machines are on that server. Now, here's the problem. I still don't know anything that's going on with that server. I have no visibility into it. I have no idea if that physical server is overused. All I get is access to my virtual machine, so I don't know that much. So I don't know the sockets on the servers. I can't see the cores. I can't get serial numbers of any. I get nothing. So good virtual option for increased security on the cloud. But what if I have a license for some custom software or enterprise software that's tied to the MAC address of my computer or the serial number of something in my computer, and it needs to see the hardware? Well, that's where I get a dedicated host. I've got full control over the hardware. I can see the underlying hardware. This is as close to I can get as data center performance level in the cloud because it's a bare metal server just like I would have. So keep that in the back of your mind. High regulatory compliance, complicated software management, this is your option. And guess where else this goes well? VMware had a really beautiful solution where you'd put your VMware servers on dedicated hosts on all your clouds. And that way, your people that were used to using VMware in the data center could use the same interface on the cloud, and it's basically they didn't have to use anything because all the cloud is somebody else's data center. There's also the concept of, say, Nutanix. Nutanix is a beautiful private cloud along with IBM's OpenStack, and you can put Nutanix Cloud directly in your data center. And with Nutanix, if you get some of these dedicated hosts that you can put in, say, AWS, Azure, and Google, your capacity could expand to any of these cloud providers, and you could use the Nutanix commands that you're used to and a business will be used to. So lots of good reasons for dedicated hosts. So how do we secure an EC2 instance? Well, there's going to be a lot that's actually going to be going into securing virtual machines. Far more than is actually covered here. But that kind of information would be covered in, say, a CISSP certification. Or, of course, we would teach it to our cloud architect students. But let's talk about doing it the way to get you to pass the exams. Because if I give you too much of this other stuff before you take the exam, you're not going to know how to answer the exam. Because if you know too much, these exams become a little harder. Because you have to figure out what they would do in the certification way versus what you might do in the real world. So I want to keep it to what's in this exam for this piece. So you can use a security group to keep unwanted traffic from getting into your system. So that's one of the ways you would do it. Remember from yesterday I said access control list, specifically network access control list on AWS, keep unwanted traffic out of a subnet. Well, with a virtual machine, you use a security group. And that basically is like a host-based firewall that says, allow port 443 traffic in for HTTPS and block everything else. So this might be what it might look like over here. You've got your virtual machine and you got your security group protecting it or limiting the traffic that could come in. So next, we'll talk about how to provide an EC2 instance and an IP address. So an EC2 instance can have multiple network interfaces. just like any server, can have multiple network cards in it. And anytime you've got more than one server in a network, for the most part, each interface, unless you're in a bridged environment, but in this case, each interface will need to have a unique VPC address space and a different subnet. You have 10 Ethernet cards in a server, 10 different subnets each card is generally on. That's why we need subnetting. And if you don't know how to subnet, my team, please drop a link to the last subnetting webinar we did. And actually, while we're at it, everybody needs to know BGP. So Chris or Tyrone or whoever's behind the scenes, drop a link to our most recent BGP workshop. That's in about 12 more hours of free networking training for you that you really do need. So when we deal with a virtual network card, we're going to get an IP address, which will give us a DNS name from AWS. And how do you access a virtual machine or an EC2 instance? Well, you can attach directly to the EC2 console. If you've got IP connectivity to it, maybe through your direct connection or your VPN, you will just SSH into your Linux machines. How do you access a Windows machine remotely? Well, you can't just SSH into it. You use the Remote Desktop Protocol, RDP, to remote control a Windows desktop. Of course, you can do some management of these systems at the software development kit. So I'm going to stop there because after this is containers, and boy, we can get into some topics there. So let me stop it and bring it to some questions. Who has questions? Can I explain more on Nutanix? What is it and what does it do? Excellent. Yeah. So the public cloud providers are renting you space in their data center. And public cloud providers have great data centers. They've got great practices, but generally speaking, it costs more to host your information in the cloud data center than it would your private. And here's the reason why. The cloud provider has to run the identical data centers that you do. So they need to buy the same stuff. Now, granted, the cloud providers get a bigger discount on the stuff than most businesses do, but they're also something that's called hyperscale, which means they need so much more management and overhead that things get bigger. Now you got your cloud providers, and some of them have 50 to 100,000 salespeople getting paid $200,000 to $300,000 a year in the sales and architects. So you might have, 40, 50,000 people doing that are just getting paid to do sales. Then the cloud providers have to do their marketing. So you can imagine you've got the same data center that you need to run, and then they need to pay a staff of, all the people to go sell it and market it. And then after that, they got to make money when they charge you for it. So that's why cloud computing generally costs more. Now, the next thing to understand is if it's next to me, it performs better. If it's 1,000 miles away, I've got latency to it. So the best performance we can ever get will be local. And the most control we ever get will be local. For example, in my private data center, I can make sure that the CEO's traffic goes first, the CFO and Chief Operating Officer next, my VP's traffic after that, my voice traffic right after that, my video traffic right after that, and then normal business traffic right after that, and anything else could be a worm or a virus, deprioritize that. We can't do any of that on the cloud. So we have much more control in the data center, much more performance in the data center, and typically speaking, lower cost in the data center. But here's the problem with the data center. It takes a lot of work to manage this. You need really smart people with a lot of expertise to basically build and run your own cloud. So what Nutanix is, what OpenStack is, it is cloud software that you stick directly in your data center. So you install the cloud software. All your servers and storage effectively get pooled together in the identical way that Amazon or IBM or Cisco or anybody else's cloud would do it. You create a virtual machine. It moves it to any one of the servers that has capacity. It's got your virtual load balancers in it. So it gives you the ability to create your own private cloud. You want to run a function as a service like serverless computing, which runs on serverless. Instead of an Azure function, instead of a Lambda function, you run the function that's available on, say, Nutanix or OpenStack. So organizations get all the benefits of the lower cost and the higher performance for their main, and all the benefits like auto scaling, like they can have extra server capacity and their website could need more server capacity, and Nutanix or OpenStack will just give it as demand. So everything in the public cloud in your self-managed data center. And then you can still connect your Nutanix cloud or your OpenStack cloud to AWS, Azure, and Google and leverage their scalability and the agility benefits that you get on the cloud, because the cloud may cost more, but it's typically more agile. So this enables you to have the best of both worlds. Best performance with your data center and the ability to go out there and use all the other clouds for the things they provide. So this is a really great solution. Can I explain the difference between bare metal and dedicated machines? So here's bare metal, straight out of the box server. So when you're getting that dedicated bare metal server, you install your software on it. Want to run the system on bare metal without a hypervisor? Because your application can't be run in a hypervised environment? You can. Want to put your VMware servers on bare metal? You can. Want to put your Nutanix or OpenStack stuff on there? You can. Want to put your managed Kubernetes like OpenShift on there? You can. Now, when you get more of the dedicated instance, these dedicated environments, what it means is only customer A's traffic is on server A, and only customer B's traffic is on server B, as opposed to the traditional tenancy, which is everybody's anywhere on any server they want on a public cloud provider. That's a really good thought there, Anna. I hope that made sense. Any others? Okay, well, we will get back to the content. So I need to know you're really awake for this, because now we're getting into containers. And you know me, I don't want to just give you what's on a certification. I want to give you some knowledge too. So I need to know you're awake. So first, I want to tell everybody that if you have not gotten the 40 plus labs that we have for you to do, please go sign up for them. They're completely free. While you're at it, please get the free certifications guidebook, if you've not done it, to talk about which certifications can boost your career if you wanted to be a cloud architect or a solutions architect, for example. If you haven't liked the video, please do so, if you're having a good time anyway. And if you're not a subscriber, please subscribe and hit the bell to be notified of new videos to help you in your career. And please do check out the section, the description section of any of our videos. We've got lots of free stuff to help you in your career. So let's start talking about containerization. So what's a container? So to me, a container is a lightweight version of a virtual machine. And as I showed you the virtual machines before, you saw we had the server, we had the hypervisor, and I mentioned that in each virtual machine, we had a copy of the operating system, the application, and its dependencies. So I don't know how many of you are very familiar with the resources that an operating system takes, but I got to tell you, it takes a lot. We may have some operating systems that take 8 gigs of DRAM just to run it, and they can use a good CPU core or a half a CPU core just to run the operating system. So if we've got a server with a limited storage capacity and we want 50 servers on something and each one takes 8 gigs of DRAM just to run the operating system, well, you can see how much memory we're wasting, how much CPU resources we're wasting just for the operating system. So what if there was a better way? What if there was a way that we could leverage the operating system and the libraries that are provided and put multiple applications all on that single server and keep those applications that are on that server all isolated from each other? So we don't need multiple copies of the operating system, but what happened in one container wouldn't happen in another container. Wouldn't that be kind of cool? So that's what a container is. So a container will require much less memory and CPU resources than the virtual machine, which means instead of maybe having 50 virtual machines on a big server, well, it might be about 300 containers on that same server. So think about less electric, And why are we concerned about electric? Because you have to understand that the electric creates heat. And these data centers get hot. And the amount of air conditioning these data centers take and power that it takes it. And, we don't have enough electricity on the planet to power half of our stuff. So we got to be concerned about it. I can also tell you from lots of experience, cooling these data centers is ridiculous. And it takes so much power. The companies need to bring in extra power from the power companies just to run the air conditioners. And of course, you need backup air conditioners, because if your air conditioners fail, your servers aren't going to be too happy. So think about that. So anytime we can do more with less, it saves us money, and we can then invest this money into new opportunities for the business. So understand that a container requires some operating systems from the library, which means a container that's designed to run on Mac OS, you can't stick on a Windows server or a Linux server because it doesn't have those operating system libraries. You cannot put a Windows-based container on a Linux host because it won't have the Windows libraries. You can put a Windows container on a Linux host. Now, Microsoft's pretty darn smart. That's why they're one of the most valuable companies in the world. I think they're the second most valuable company in the world. Here's what Microsoft did. They created something called the Windows subsystem for Linux, which is an Ubuntu Linux kernel, which they put into Windows 11. So now with Windows Server, you can actually run Windows containers and Linux containers. So that is the exception to that rule. So generally speaking, when we deal with containers, we need something to kind of orchestrate the containers and keep them going up and running. And we're going to have some options here, and we're going to talk about the reality of these options. If we were going to only be on AWS, which is 2% of the customers in the entire world that are only on one cloud at this point, of enterprise customers, I would tell you that Amazon has the most simple and beautiful and elegant solution in the world called Elastic Container Service. And that Elastic Container Service will orchestrate your containers. And if that's your case, it's very simple and elegant. Problem is, if you use Amazon's Elastic Container Service, and then your business changes, and you want to use more than one cloud, you're stuck in this proprietary container orchestration. So we will later talk about Kubernetes, which enables you to run in all clouds. But if you were just on AWS, if the business needed that particular use case, and that business wasn't concerned about vendor lock-in, and they weren't concerned about their future and the agility to move to other clouds, you could use Amazon Elastic Cloud's Container Service, and it is very simple, and it is honestly very elegant. And it provides a fully managed container service for you, which is high availability, 99.99% available. It's deployed in a VPC, which means you can use access control lists and security groups for your network traffic. And it will orchestrate your containers in either virtual machines or in a serverless environment called Fargate, where you put your virtual machines in this serverless environment and it runs on their servers, and they hide that from you. And that's, a level of abstraction you don't think about. So you don't have to think about managing servers and patching servers. So here's what it would typically look like if we were to use this proprietary orchestration system. We would build our containers, we would deploy them, we'd provision them to where we're going to put them, and we isolate our containers, and we manage the application. By comparison, if we were going to use this Fargate thing, we would basically use this to the container. We build the container and just stick it on Fargate, which is going to be a managed container service, managed compute. Now, lots of time it's used with Fargate. Again, Fargate's going to be completely serverless, so there's nothing for you to think about. Generally speaking, with serverless, it gets real expensive when you use it, and it's cheaper if you don't use it, where virtual machines are the same price whether you use them or not, so you got to figure out what makes sense. And when you use a service like Fargate, you have no control, where you've got much more control if it's on a virtual machine, like an EC2 instance. So the architects will need to determine what's best for that business case. But if it was Fargate, it gets pretty simple. Here's what it would look like. You basically have the Elastic Container Service doing the orchestration, and Fargate itself will basically be where you put the containers, and then you pay for what you use. Here's the things to think about with ECS or Elastic Container Service. It is fully managed, so you need a less sophisticated team to use it, which could potentially mean lower employee costs. It could be higher costs, but lower employee costs. It auto-scales, it load balances, much like Kubernetes, but it is a simple proprietary thing. You basically can set up task definitions, which means you're going to define tasks and which set of containers are going to run together on the same host. And you'll use some JSON formatted definitions. And you can use services to run or maintain a specific number of tasks. And that way you can ensure your application is always up and running. We can talk about cluster management. ECS will help you manage a cluster of either EC2 instances or Fargate containers running the system. And it will handle scheduling the containers and placement of the containers on your cluster. So you put it on a server that has it. Space for it. The nice side of ECS, Elastic Container Service, is it integrates into AWS services because it's an AWS product. So it's pretty seamless with your identity and access management systems, your VPC, nice integration with, say, CloudWatch, your load balancers, even the container registry like Elastic Container Registry, which we will talk about at some point. And this is going to give you secure and scalable networking options with your VPC, at least with the security group anyway. So it's going to give you some very good deployment and rollback options. ECS, if you're going to do, say, a blue-green deployment or any kind of rolling update, you can use a container orchestration platform like this. Gives you the ability to roll back to previous versions if things don't work. It's got some networking options like bridge networking, host-based networking, and VPC networking. And that way, you can have containers that can also have their own IP addresses if they need to connect securely to an AWS resource. So how do you set up ECS? Pretty easy. You set up your environment. What you do is you create your cluster in the Management Console CLI or Software Development Kit. You choose whether you want to put your systems on EC2 instances or virtual machines to give you control of the underlying infrastructure. Or if you don't care about control, give it to AWS Fargate and you've got some simplicity and elegance. Then you define your task tech definitions. You create your test definition that'll specify maybe the Docker image that you're going to use, the CPU, the memory requirements, the networking mode, and any other configuration details for your containers. And then you launch your services. You use the console or the CLI to create your services and launch them, and define the number of task instances you need. And if you're going to use more than one, configure your load balancing. You monitor it, you manage it, and as necessary, you scale it or you update it. So it's a pretty simple way to do things. Let's talk about some best practices with ECS. You're going to optimize your test definitions. You really want to carefully configure your resources, your CPU, your memory, for your tasks to be very efficient. You may want to use environmental variables and IAM roles to securely manage the configuration and permissions of your system. Maybe put in some good secure networking, Use VPC and security groups to isolate your traffic and resources. Ensure that your tasks are running in private subnets with controlled access to the internet, public internet especially. Monitor. You're not going to put anything out there and then not see what's going on. So monitor and log effectively. And look at those CloudWatch logs. Do something to aggregate them. And when possible, integrate it into the organization's DevOps or CI/CD pipelines. And that way, you can automate the deployment of new container updates. You can configure auto-scaling policies to deal with variable workloads. All right, that is Elastic Container Service. The next thing we're going to talk about is a little bit more complicated. And give me a hashtag Kubernetes. And then I'll know that you're ready for this. Because I'm going to give you a little more on Kubernetes than, when I say a little more, I mean a whole heck of a lot more than you would actually get in an AWS Solutions Architect Professional or Associate certification. But it's important knowledge.
Hey, Mike, I got one question I want to do before we get into the good stuff. And then we'll just do this one question, and then we'll save the rest for
sure.
All right.
What kind of images can you run on ECS? Container images. So whatever the containers are that you guys have. But you have to understand that ECS is just orchestrating where the containers will be and their placement. All right, so Kubernetes, you strapped in? Did I see those hashtags, Kubernetes? Did they come in, Chris? I want to know everybody is awake. Okay, Alonzo Coleman gave me the first one. Adrian Flores, Kubernetes. All right, Miriam Flores, Kubernetes. Fantastic. Nate, Kubernetes. Jose Cruz, Kubernetes. And Moses. Excellent. So now we're going to have fun and talk about Kubernetes. Now, I want you all to give it a thought for a second. And this is why we're going to talk about Kubernetes ahead of the Amazon proprietary Kubernetes things, or at least the Amazon managed Kubernetes things. If Kubernetes is orchestrating your containers, and you are in the AWS cloud, the Azure cloud, and the Google cloud, and you use, say, AWS's Kubernetes container system and AWS crashes, what happens to your container orchestration in Google and Azure? You got nothing. So after we talk about Kubernetes, tomorrow we'll give you the options that you can choose to or not. But if you have a standard managed Kubernetes thing like OpenShift from IBM and you have it in AWS, Azure, or Google, and one or two of your clouds go down, it doesn't matter. The other cloud will take over. You'll have auto scaling and you'll be in good shape. So Kubernetes is going to be really important in the multi-cloud world. Kubernetes is good in the data center. For the private cloud, it's good in the public cloud. And if you create your own clusters, it'll work anywhere. So let's talk Kubernetes. So Kubernetes, which you may hear of as K8, is an open source container orchestration platform. Kubernetes is designed to automate deploying, scaling, and operating. So if you think about what an architect does, the architect itself kind of orchestrates the team of people to design a solution to improve business performance. If you think about the conductor and the orchestra, they're basically orchestrating, okay, the flutist, you get up, you get quieter, the harpist, you do your thing, and they're guiding people with pace and tempo. Well, with Kubernetes, it's the same thing that we need to do. So it's orchestrating the container. So always remember that Kubernetes is a container orchestration problem. So when it comes to these types of plans, we typically have something called the control plane and a data plane or worker plane. So the control plane does the control. The work does it. So if you look at a network, you might understand that the network has routing protocols. That is the control plane. You may notice that routers have links. That is the forwarding plane. If you go to the AWS Management Console, that is the control plane for AWS. The server which you put your web server on is the worker plane or the data plane. So with with Kubernetes, we're going to have a control plane, which is going to be called the master node. And we're going to have the worker plane called the worker node. So this is your high-level Kubernetes architecture. So now we'll talk about the various elements in Kubernetes. And they're plentiful. It's nowhere near as complicated as networking, but there's some meat to this. So that master node is going to be the most important part of the cluster because it's responsible for orchestration. And if that goes down, things will happen. So the master node hosts the control plane. So it's the orchestrator of the system. So if we have 3 containers and the master node were to go down, those 3 containers can still run. But if a container crashes, we're not going to start a new one. If we need the system to scale out because the containers need more capacity, it won't work. So that master node or that control plane is so critical that if you've got a multi-cloud Kubernetes environment, you're going to need some industrial Kubernetes that's going to run in all clouds versus a cloud proprietary one. Now, the worker nodes, these are the machines where the containers are, those virtual machines. And the containers applications are going to be pods, or where the pods run. So they are critical too. If you don't have anything controlling it, you've got nothing. If you don't have the computer or anything that can do the work, you still have nothing. So let's talk about the components of the master node. That control plane, the first component is going to be an API server. Why does the Kubernetes control plane need an API server? Well, that's going to be the front end of the Kubernetes control plane. It's going to be used by all other components of Kubernetes to interact with that cluster. It typically processes RESTful API requests. If you're familiar with RESTful APIs, it'll validate them and it'll update them with the corresponding objects in something called the etc data store. The etc is going to be a distributed reliable key value store that Kubernetes will use to store all the information, including its configuration data, state data, and metadata. Does that sound like a database to you? And the whole point here is to store the entire state of the cluster, and that's why it's another critical component. Now, we also need something called a controller manager. And the controller manager is going to run the controller processes that are going to regulate the controller. So the controller manager is going to watch the state of the API server. It's going to make adjustments to get it to the desired state. The controllers will include node controllers, replication controllers, endpoint controllers, and others. And then we're going to have the scheduler. And the scheduler is going to assign tasks to the pod. And its function is to ensure that the nodes are placed with sufficient resources according to constraints, whether it be things like affinity or anti-infinity. So what's this kind of look like when it's put together? You can see this is a beautiful diagram, so you know Alonzo from my team joke because he makes beautiful charts here. So you can see in that master node, we've got the scheduler, we've got the kube controller, we've got the API server, and we've got that cloud controller module. And we talked about that etc.d, or that etc.d. You can also see on the worker node, and we're going to talk about this soon, we'll have the kube proxy, kubelet, the container runtime, which is what's necessary to run the container, and of course we'll have the pods, which will have the containers. Now, generally speaking, this host kernel there is because the pods are going to be running on a virtual machine, and the kernel is going to be the kernel of that operating system. You know, that part of the operating system that manages memory, CPU resources, schedules tasks on the CPU, that kind of thing. So what's the flow? So the interaction flow is going to be, it's going to come in as an API request. Whether it's a user or an administrator or an automated system, it's going to make an API request to the API server. And that's going to happen anytime you need that needs to be create or modify or delete a Kubernetes object, whether it be a pod or a service or deployment. And you can see here, you know, the way that API request is going to come in and where it's going to hit the API server. The next part of the interaction flow is going to be related to state persistence. The API server is going to validate the requests, and it's going to persist a new state in that etc.d. So, you know, you can look in this particular environment where it's going to persist it, and that way you can get access that can get access when needed. The third part of the interaction flow is going to be monitoring of the state. The controller manager is going to need to monitor the state of the cluster and work to make sure that it gets brought to the desired state of the objects that would be in that etc.d. So you can see what's going on here. Not really sure what happened with my screen over here, but you can see, you know, the cloud provider's API. You can see the control plane. You can see where the nodes are, where things are being done. Or at least the... And the next part of this is going to be task assignment. We're going to have this scheduler that's going to create new pods when appropriate, because we might need different resources. So, you can see what that looks like here. And then, of course, we're going to have some node communication here. Each worker is going to have its kubelet, which is going to have to communicate with the API server to receive the state information. So, we're going to have this communication flow between our nodes. And you can see in this diagram, some of that communication and how it's actually working between the nodes. So now let's talk more about the worker nodes. If the master node was the control, the worker nodes where the work's done. So Kubernetes worker nodes are typically speaking going to be virtual machines. Could you put it into some sort of a Fargate environment? Yes, you could. But typically speaking, you're going to put this in a virtual machine. So when it comes to Kubernetes, the worker nodes are where the pods are. And that's going to be the smallest deployment unit in Kubernetes. And each pod may have one or more containers in it. When it comes to networking, the worker nodes are going to get involved in all networking aspects of the pods. Communication between pods on the same node, communication between pods on different nodes, and any kind of external communication. Because think of it almost as like an end device. And if an end device is out there, whether it's a server or a container, it's still going to need to talk to the network and talk through the network. And we can talk about resource management. These worker nodes are going to manage the local resources, like the CPU, the DRAM, the storage, and then allocate them to the pods based upon the requests. And you're not going to go beyond the limits that you specify when you create these pods and their definitions, because you're going to give it a limit of CPU resources and DRAM resources. And then you could add more instances as needed, but you're going to specify what they have. And of course, these worker nodes are going to be like your end system, and they're going to collect logs and metrics from the pods and the containers. And there's tools here that you can use to kind of look through this and help you manage it. Things like FluentD or Prometheus. And there's plenty of others that can be used for monitoring and logging as well. Now, another component of the worker node is the kubelet. And the kubelet is going to be the agent that runs on each worker node. Its function is to ensure that the containers are running in a pod exactly as specified in the pod. So the kubelet's going to communicate with the API server to get the pod specifications, and it's going to ensure the desired state of our containerized applications. Next would be the kube proxy. So the kube proxy is going to be a network proxy that works on the worker node. It's going to maintain the network rules on the nodes, enabling the networking communication to the pods from inside and outside. And, kube proxy is going to manage IP routing, load balancing. So I always thought of the kube proxy as kind of like the networking. And of course, we have to have the container runtime. So when we have a container, it needs to run somewhere. So container runtime is going to be the software that's responsible for the containers. An example of container runtime options could be things like Docker, Containerd. So you're having the orchestration control of this, but you got to have a runtime module to run your containers. And that's why we often have the interplay between Kubernetes and Docker together. Now, the Kubernetes worker nodes also have to interact with the master node. And that's where this API server communications come into place. The worker nodes are going to communicate with the API server on the master node. They'll get their state information, their updates that way. The scheduling needs to occur. The scheduling is going to be on the master node. And then it will assign work to worker nodes based upon resource availability or other constraints. And we have this concept of a control loop as well. And the kubelet on each worker node is going to be constantly interacting with the API server in order to ensure that the desired state of each pod is going to be maintained. Let's talk about the life cycle of a pod on a worker node. First thing that's going to happen, it's going to be scheduled. The scheduler is going to assign a pod to a specific worker node based upon resource requirements and policies. The API server will have a notification. The worker node will be notified of its pod assignment from kubelet. and the container runtime will instruct the container runtime to pull the necessary container images and start the containers. What I'm going to do is I'm actually going to show you a container runtime. I'll draw it out architecturally for you after this. And of course, the network setup. So the queued proxy, because it's the networking component, will set up the necessary network rules to allow communications from the pod. And of course, we're going to have the monitoring and management. So the kubelet will monitor the containers to ensure that they are healthy. And what they'll do is they'll report their status back to the API server. Now, I know I talked about it initially. I'll talk a little bit more about the kubelet. And the kubelet is going to be an agent that's going to run on each worker node. It's going to monitor the pod. It's going to watch over the pod, which is basically the smallest deployable unit in Kubernetes. And it's going to assign it to its node. It'll ensure that the containers inside these pods are going to be running healthy. So here in this particular environment, you can kind of see the way these things are sort of interacting here. And while I'm at it, let's draw out what this really is going to look like. So you get the concept of this container runtime. And I'll show you what you typically would see in a cloud computing environment here. So in this particular environment, we're going to have the physical server itself. And if it's in a cloud, you're going to have a hypervisor in most cases. Unless you buy a bare metal server. And then you're going to have your virtual machine. So let's make this a really big virtual machine. And I'm going to make this a huge virtual machine instead of having multiple virtual machines. So let's say this VM has got 256 cores and 4 terabytes of DRAM. This thing is going to store a lot of containers. So that's your virtual machine. And then your virtual machine is going to have its operating system. So here this virtual machine is going to have its operating system. Let's say it's Red Hat Enterprise Linux. And then we need our container runtime module. And this typically is going to look something like Docker over here is going to be here. And then we'll have container A, and then we'll have another container, call it container B. And then we'll have the third container, which is, say, container C. And by doing this, you can see that all these containers are, for the most part, separated from each other. And we can put a lot of these containers on that same virtual machine. So I hope that kind of helped with the container runtime. So now let's talk about some other key components. We'll talk about a pod, a service. We'll talk about volume, namespace, and config and secret. So I previously mentioned the pod, but a little more because this stuff's a little icky and complicated. So I want to go over it a few times to make it sense. A pod is going to be the smallest and simplest Kubernetes object. Again, it represents that single instance of a running processor in your cluster. The pod will encapsulate our containers, and it typically will contain more than one containers, or one or more containers. And usually maybe one, sometimes more, but they're going to be tightly coupled to share resources like storage and networking configuration. And the containers in the pod will have the same IP address, host name, and networking resources. So same IP address. So we'll have multiple pods with different IP addresses. A pod can typically share the same storage volume as well. Now let's think about lifecycle management. So Kubernetes is going to manage the lifecycle of the pod. So maybe we need 5, and it makes sure that we only have 5. Maybe we have 2, and it thinks we need more at a time, and it will scale out for us. So what's a service? A service is going to be an abstraction that's going to define the logical set of pods and a policy for accessing the pods. So what's a service going to do? It's going to give us a stable IP address and a DNS name to access a set of pods. Because we need to be able to reach it. The service will provide load balancing. I've always thought of the Kubernetes service as a load balancer, and it will direct network traffic to all pods behind the service. Now let's talk about some other things and what does a service do. Let's talk about the cluster IP. That's going to expose the service on a cluster's internal IP address, an IP address that's going to only be accessible within the cluster. We're also going to have the concept of a node port, and that's going to expose the service on each node's IP address and as a static port. And that's going to be what makes it accessible from the outside. So it will also provide a service name to a DNS address. Kind of hope that sort of makes sense. Now, we also need to talk about a VM. So what's a VM do? VMs are going to provide storage that will persist beyond the lifecycle of the containers. So when you mount a storage VM in a virtual machine, it's the same thing you're doing here. So if your container restarts, it's going to be able to access the same data. So let's talk about types of VMs. We can have an empty directory, and that's going to be temporary storage when the pod is created and assigned to a node. We're going to have the host path, and that will mount a file or directory from the host path, from the host node's, say, file system to a pod. We will have a config map and a secret under a VM types, and that's going to provide configuration data and maybe sensitive information like passwords. And then we'll have the persistent VM and the persistent VM claim, and that's going to be a way to request and use storage resources that are not tied to the life cycle of the pod. Now, we have this concept of a namespace, and a namespace in Kubernetes is a way to divide our cluster resources between different users and applications. So what does a namespace do? It's going to help us organize and isolate resources like our pods, our services, our deployments, because each namespace is going to be like our virtual cluster in the main cluster. What else does the namespace do? Access control. We can apply identity and access management policies to the namespace, and even role-based access control, which we'll talk about when we get to the identity and access management section of this course. And it helps make sure that we don't have naming conflicts, because it'll allow resources with the same name to kind of exist in a different namespace. So it'll help figure us out for us. So let's also talk about config map. And what is config map in Kubernetes? It's going to be that object that enables you to store, say, non-configuration data in a key value pair. And the config map will help you with configuration management, because it'll store your configuration settings that your applications will use, whether it be configuration files, command line arguments, and environmental variables. It'll decouple your configuration, and that's basically to take your configuration settings and kind of decouple it from your application code. So that's going to make it a lot easier to manage and update your configurations when you need without recoding the application. I mentioned secrets. So the secret is where you keep your secret stuff, right? So your OAuth tokens, your SSH keys, your passwords. And you're going to use the secret in Kubernetes for sensitive data storage. This is going to give you that way to store and manage your sensitive data, because you don't want to make sure that it's exposed in application code or container images. And let's talk about access control. We can use that to reference the pods to access sensitive information securely. Let's talk about deployments. So in Kubernetes, we have the concept of a deployment. And the deployment is going to be used to manage replica sets. And this is going to ensure that a specific number of pods are going to be running at all times. So if we've got a pod that goes bad, we can add a new one. So rolling updates, rollbacks, that kind of thing. Let's address briefly replica sets. And that's going to be there to ensure that a specific number of pod replicas are running at any given time. You often use a replica set and it's often used by deployments. So you can orchestrate the pod creation, scaling, and deletion. And of course, a daemon set. A daemon is like a lightweight thing that runs in the background. And that's going to ensure that some of the nodes can run a copy of the pod and that all nodes are added to the cluster. And I'll briefly talk about a stateful set. And that's going to be managing the deployment and scaling of the pods. And it'll provide guarantees about the ordering and uniqueness of the pods. Think of it where maybe a stateful application like a database. And we'll talk a little bit about the cluster IP, which is going to be the default type. And this is going to expose the service on the cluster's internal IP address, meaning only accessible within the cluster. So let's talk about a load balancer. And that's going to be used to expose the service externally by using any kind of cloud provider's load balancer. Now, a little bit under networking, we can think of ingress. And ingress is going to manage external access to the service coming in. It's going to provide load balancing, SSL termination, and name-based virtual hosting. All right, so we did a basic overview of Kubernetes that is about as quickly as we possibly could. So actually, while we're at it, I have the opportunity to just go through Amazon's Elastic Kubernetes service and its features, and then I will take questions because I feel like it's going to be hard to go talk about Kubernetes now and then tomorrow talk about the Amazon proprietary features. So bear with me an extra few minutes. So in a multi-cloud environment, you're going to need a multi-cloud managed Kubernetes environment. Many organizations use IBM OpenStack because they can put it in AWS, Azure, Google, Alibaba's cloud, as many clouds as they want. And that way it's there, and if any cloud goes down, you don't care. If you were only going to be in Amazon, and you weren't concerned that if the Amazon cloud went down, your Kubernetes cluster couldn't have a control plane in your other clouds, you could use the Amazon EKS service. And it's going to automate the management and setup and availability of Kubernetes because it's a pre-made managed service. And that's going to bring with it more simplicity and elegance than Kubernetes, which we talked about, which is somewhat complex. Nowhere near as close to networking, but it's somewhat complex. And it's going to be integrated into every AWS service. So it'll work with your load balancers, your identity and access management systems, and CloudWatch. It's a high availability, high security control plane. So as long as AWS is up, for the most part, it will stay up. Of course, a hacking event, a major networking failure, a control plane failure will obviously take this down. And if this is running in AWS, it'll take down all your other cloud stuff from a control plane perspective. What's running will be there, and nothing else will be able to up, go down, or control. Same thing if you used Azure's Kubernetes service or Google's Kubernetes service. When you only have one point, it becomes a single point of failure. The cloud provider. So Amazon EKS makes it pretty easy to upgrade to different Kubernetes versions with minimal downtime because it's managed. It's going to scale great because it is a great Kubernetes service. Once you get past that architectural limitation of only working on one cloud with 98% of your organizations using multi-cloud, this in and of itself is a very great managed Kubernetes environment. And it's simple to use. You create the cluster in the management console. You specify the Kubernetes version you want and your VPC configuration. You configure your IAM roles. You provision your worker nodes and where you want them to be, usually on virtual machines. Tell the worker nodes to join the EKS cluster. And you deploy your Kubernetes application. And you monitor it and you scale it as necessary. So that's the Amazon proprietary one. Now, Amazon also has this concept of an EKS distro. And this is the distribution of the Elastic Kubernetes service. And this is a way that you can run your containerized applications in the data center the same way you would in AWS. It enables you to create Kubernetes clusters with the exact version used in Amazon. Main difference between EKS and EKS distro is that EKS is a fully managed Kubernetes service on AWS. Whereas EKS distro is something you can download and install in any environment. So that's always an option for you. In this way, a user can deploy Kubernetes clusters that match their AWS ones without having anything to worry about. And in a hybrid cloud between just AWS and the data center, this could be a great environment. And that's really what it's designed for. And let's think of a hybrid environment. When your data center needs more capacity, additional nodes could be added on for AWS. EKS Distro could be great in disaster recovery. You could use EKS to back up your data center, and if your data center goes down, AWS could take over the load. It can be deployed in lots of places. And then there's the concept of EKS Anywhere. And that is going to simplify a customer's on-premise Kubernetes cluster management via default configurations and gives you the same kind of auto-scaling self-healing you get with Kubernetes. It's going to give a consistent and reliable cluster environment on-premise. And, it's going to be easier than a self-managed environment. It would reduce support cost, potentially, and it's open source with support from AWS. Actually, let's finish with Elastic Container Registry because that's quick. The Elastic Container Registry is going to be a fully managed container image registry provided by AWS. So it's going to make it real easy for developers to store, manage, deploy their container images. And that way there's a good, secure place to put them. It's fully managed, so you don't have to think about setting up your own container registry and managing these types of things. It'll integrate with other services, so it makes it simple. It'll integrate with whether ECS is the proprietary one you're using, some form of EKS control plane, Fargate if you're not putting your systems on virtual machines. It supports into the AWS Identity Management Console because guess what? It's an AWS service. It provides encryption at rest, access to the key management system, designed to be highly available. And it's designed to simplify image management, provide lifecycle policies to automate the cleanup of unused images, helping to manage your storage costs. It can do some image scanning where it can look for vulnerabilities in your container images to help you identify and potentially remediate security issues. So let's bring it open for questions. Does anybody have any questions for us? What Tyner container runtime engine does KH use? I heard it does not use Docker anymore. You can use Docker, and it does have its own form, but many people use Docker. But, are you referring to EKS or are you referring to Kubernetes itself? EKS itself, the Amazon version, uses containerd. And that's going to be a container runtime engine that's typically used instead of Docker. You can still run your Docker images on EKS. But you can also, by default, it's using containerd. Containerd is rapidly becoming an industry standard runtime module that's going to manage the complete container lifecycle. So typically it's that. It's typically used because it also supports the Open Container Initiative, which means you can run your Docker images and your container D and your other container images with containerd. What programming language would you use to communicate with engineers? Well, it all depends. So if you're an architect, you don't use any programming languages and you communicate to engineers in clear language. I need 10,000 virtual machines that each have 32 cores, 64 gigs of DRAM, and half terabyte hard drives with 2,000 IOPS. That's communication. So if you want to be a software developer, you will need a programming language. If you want to be a cloud engineer, you will need to learn certain programming languages. If you want to be a, what's the word I'm looking for? If you want to be a DevOps engineer, you will definitely need to know programming languages. But if you're a cloud architect or a solution architect, if you're a project manager, if you're a sales rep, if you're a manager, a leader, you probably won't need to know coding languages. So it's all really about what are you trying to do. How do you ensure security is implemented on Kubernetes? So First, remember, there's a lot more security you need than just Kubernetes. You will need to control your network access. You will need identity and access management systems. You will need encryption. You will need firewalls in the right places, IDS, IPS systems in the right place. And we can't pull Kubernetes security out of the full security posture. But if you're asking just Kubernetes security, we can use role-based access control. And role-based access control is a form of identity and access management where you group people into roles. So what do I mean by that? Let's say a company is like Amazon and they have 1.5 million employees. You could manually have people there and say, Mike gets this permission. Chris gets this permission. Mark gets this permission. And in order to do that for 1.5 million people, you're going to make a lot of manual errors and you're going to need a lot of people. Role-based access control is, let's group our people into systems administrators, and every systems administrator gets the same permissions. Finance people all get the same permissions, and it scales. So that way you create a group of people, then you create the permissions, and then you assign users to that group. So that's going to be the way. So we're going to use role-based access control. We're going to enforce network policies to control the traffic between the pods. We're going to use secrets management to securely store our sensitive information. We are going to regularly update our Kubernetes environment to keep it up to date. We are going to work on good pod security policies. We will define security context and permissions for the pods. We will enable audit logging to track access and changes to the cluster. We will implement TLS security to make sure that the data is encrypted with TLS, the old SSL, but it's now been modified to TLS security. So those are some things we can do specific to Kubernetes, but we're still going to need all those other security things. How do you manage ephemeral containers in the applications running it? Well, typically, to manage ephemeral containers in an application, we can use Kubernetes jobs for short-lived containers. We can use a serverless function for like an event-driven or an ephemeral workload, like an Azure function or an AWS Lambda function. Typically speaking, we can use Kubernetes to handle the scaling or restarting the containers or managing the life cycle of ephemeral containers. You can bring in the next one, Chris. How do you scale Kubernetes in AWS compared to how do you scale them in virtual machines? The identical way you would do it, and we've done it since Kubernetes has been around. It doesn't change at all. Same Kubernetes control plane. It's a standard. Same worker data plane. So you don't. Except in the cloud, you could potentially use Fargate if you wanted to give up control. Any suggestions for freshers who's sick for interview and coming from a non-completely background? Absolutely. So first, your background is meaningless. What you choose to learn is there. What's your goal career? That's the first thing. Because the first thing we need to do is give your goal career. If you can provide that, I can give you information. Because if you train to be an architect, you will not be prepared to be a cloud engineer. If you train to be a cloud engineer, you will not be prepared to be an architect. If you plan to be a lawyer, you will not be prepared to be an airplane pilot. So first we need to know. Then after we know your career, we have to define your career. Is it a planning career, like architecture or strategy consulting? It is a worker career, like engineering, where you're actually doing the work. Or is it more of a technician career, like cabling or a cloud admin type thing, where you're basically just configuring things without the depth of why you're configuring and what you're doing? So we need to first understand that. The second thing is get the right training. When I left internal medicine for tech, I got a lot of training. And, it was expensive, but that's how I did it, because I knew that every day I wasn't working, I wasn't earning. For example, and I've gotten lots of freshers, solutions architect and cloud architect jobs. But, the average cloud architect earns $1,000 a day. So when I started my career, I wasn't going to try and save, a couple of $1,000s to spend 9 months earning when I could have earned $20,000 a month. So kind of think about that in the back of your mind, getting the right training, but it doesn't matter. And you can get any job you want. And I'll give you examples of certain people who've gotten certain jobs where if you desire, but we have to know where you're from. Next side of it is really get some good interview training. I've hired people generally speaking, we need someone that can do the job. And this is what hiring managers look for. Mike, I want someone that can do the job. And I'm speaking of thousands. I need someone that communicates well. I need someone that's energetic, enthusiastic, and passionate about the work. I need someone that's willing to go above and beyond. I need someone that's emotionally intelligent. And I need someone that's a good team player. So when you're new and you can't compete with the others, you better get that stuff right, because that's how you get hired. Look, my first job was a senior engineer after leaving internal medicine. And 3 months later, I was the lead architect. And 6 months later, I was a senior network architect. And 2 years later, I was a principal architect. Why? Because I learned my job. So there's that. So if you tell me what job you want, I can guide you there. But without it, I don't know whether to send you to flight school or law school. And I'm not joking. These careers are that different from each other. What's the difference between a load balancer and ingress? Well, you bring in some really tough, good questions here. So a load balancer is going to distribute your incoming network traffic across multiple servers or virtual machines. Ingress in Kubernetes is going to manage all the external access to a service inside of the cluster, typically providing, say, some HTTP or HTTPS routing. So I typically think of a load balancer as general traffic distribution, and I think of ingress as managing and routing the traffic into a Kubernetes cluster. Testing perspective, which cloud certification will be perfected at intro level? Could you tell me what your goal is? Because the right intro level is dependent upon your goal. Generally speaking, a professional level certification, so after interviewing thousands of people, I can tell you that there's basically a 1 in 20 chance when someone has a professional certification, they know enough to do the job. And with an associate certification, basically a 3 in 100 chance that the person could potentially do the job. But I've hired people with 0 certifications many times because they were great. And there's going to be a point in your career where you're going to have to take the certifications off of your resume. In many cases, your management will want you to, because if you're going to move into an architecture role, a CEO isn't going to talk about being AWS certified, for example. And an executive architect wouldn't be either. They'd be focusing on more. So what is your goal? What is your gold job? The gold job will determine your brand, what you need to progress, what you need to share. So if you can provide that, I can answer it. But without it, I can't give you any information. Which drug does the doctor prescribe for a medicated condition? Don't know what the condition is yet. Okay, so I will tell you that there is a completely free document on which that I'd love you to download. It's in the description of this video on the chat box, which will give you the information on which certifications would help you if your goal was to, say, be a cloud architect or a solutions architect. So, did you all have some fun today? Give it a like and subscribe to the channel and hit the bell to be notified. Did we cover a lot of stuff far beyond what's in a solutions architect, associate, and professional? Yeah, we did. But I wanted to give it to you because I really want to give you guys a really good experience. If you haven't downloaded the labs or signed up for the labs, please go do so. Yorgos, Kalispera. It is so nice to see you here. Found somebody speaking my own language in the chat box, and this always makes me very happy. So I hope you all enjoyed us today. Thank you for coming. Give me a hashtag, AWS SAA. And that way I know that you're awake, alert, and oriented. It was so nice to see you all today. coming from all over the world. Yorgos, are you in Greece? Are you in the US? But it's super nice to see you. I know where everybody are in Europe. I know where so many others are you. It's been an honor to spend the afternoon with you. Thank you all for being here. Take care, everyone.